but then I was going to move us toward discussion. And the plan for this, giving me a chance to drink my coffee and wake up a little bit, is to have discussions on some of the talks, any kind of thoughts that we had from the previous day's talks, questions that people might have. Hopefully I want to see how well this works. So if you have questions, you can either raise your hand or start talking. One of the things that impressed me about the talks from yesterday was, how many there's a lot of pieces of physics and numerics. So we had talks, we were talking about some of the numerical issues. We had talks about the neutrino physics that often we don't include in the calculations that need to be included because they make a difference. And we had even talks of how much they do make a difference, the details make a difference in what we actually observe. So this is one of these rich problems where there's a lot of issues that we need to work on to get the right answer. And I think that the great news with that is, I think that makes them excellent probes for our understanding. The bad news is that it makes it a hard problem. And one of the things that I would love to get out of this meeting as a whole is kind of what are the issues and what should we be working on, and maybe even coming up with a list of here's some of the main problems we need to solve to push this field forward. So I would open up, any discussion on that would be useful to me, and I'll stop talking here and let other people give their thoughts.
Definitely user specific. It just so happens that every user gets it.
And maybe for yesterday's speakers, one of the questions I have is how soon will we get more accurate what's the time frame to getting accurate models for some of these things? Like when will we be able to say, oh yeah, I have a merger of a 1.2 solar mass neutron star and a 1.6 solar mass neutron star, and I know the ejecta mass to say even 30%. Are we even close to that? Where are we at on getting accurate ejecta masses as a function of the neutron star progenitor mass?
So Chris, can I just say something on that?
Yeah, I was going to call on you if no one else spoke.
Okay, so yeah, I would think actually we're not that far away from the dynamical ejecta. I think there are now all kind of methods, resolutions are getting better, and the numbers are not that different anymore for the dynamical ejecta, I think. But the thing we still don't know very well is the equation of state. But I think what is much more difficult are those secular ejecta that come on timescales that are very difficult to reach numerically if you have to follow several seconds and your numerical code can only take time steps of 10 to the -7 seconds, then this is a major challenge. But the other thing is also you need to, if you really want to get this right, you need very, very large resolution for that. And there are many in the wake of the first detection, many people came also up with other ways to eject a lot of material by implementing some ad hoc viscosity, which parameters that I think are not terribly well under control. And to get convergence on that, I think this may take us probably a decade or so more. But I think just the dynamical ejector, so the stuff that gets just ejected by GR plus equation of state, I think in the next few years, this number will hopefully be nailed. But then neutrino-driven winds and magnetically driven winds and long-term disk unbinding, I think this will take this will take a while until we have converged numbers there.
And it had always been my impression that the dynamical ejecta had low enough, it was neutron-rich enough that the yields were relatively, or there was less uncertainty in the yields. I think we'll have some talks on the nuclear physics to show that there are some uncertainties, but is that still the case? Is it neutron-rich enough that it gets a little bit simpler as far as the nuclear yields?
If I see Jonah also has a comment on that, but maybe if you just may answer your question. If we talk about the tidal ejecta, then I think this is still the case, because that stuff that is ejected has electron fractions of something like 0.04. And it's super robust until you get maybe 2 electron fractions of 0.2 or so. It gets a bit trickier by the dynamic ejecta component that is produced in shocks, because that then depends more well, it also depends sensitively on the equation of state. If your neutron star is smaller, then you have a larger velocity with which you collide. If the equation of state is softer, it's easier to shock. And to make things even worse, the regime, how you kick this out is, of course, also numerically a terribly hard to resolve regime, because you have to really resolve properly this enormous gradient on the neutron star surface to vacuum. This is where your shock wants to push out the material. And this is both challenging because the physics is not fully under control, and it's numerically a very challenging problem. But I stop here, and I think Jonah was next and Charles after that.
Yeah, I wanted to just second everything Stefan said as far as the sort of the long timescale stuff. I mean, the disk winds and neutrino-driven winds off a neutron star surface, and the shocked squeeze ejecta. I don't think we have any of these under control, really. And on top of that, there are very few integrated models that attempt to combine them. So not only do we not have each individual component under control, but very few people have even tried to say, well, this kilonova is coming from these 3 components in this ratio. I mean, once we have those components under control, we also have to figure out how to integrate them into a light curve model, for example. So I think we're very far away.
Yeah,
Chuck, do you want
to? Sure. Wanted to suggest something. The disk physics and the long time physics, maybe there's a way to separate it out by asking instead of the amount of ejecta, ask about the lifetime of the remnant, the time before collapse to a black hole. When will we have convergence and simulations on that, and what observables can constrain that?
Yeah, I would say that's as hard as getting things like the disk wind correct, for exactly the same reasons. We don't really have a good handle on the angular momentum transport happening within, say, a hypermassive neutron star. We don't even know whether the dominant mechanism for it collapsing is the MRI or neutrino cooling or what. So I think that's going to happen naturally as we get better at these long timescale modeling.
Maybe if I can
maybe it separates the low density physics from the high density physics?
Sure, that's true. But I'm not sure that, I mean, the nuclear equation of state, this changes between those two regimes, as does some of the neutrino physics. But from the perspective of, say, magnetic fields, I don't think it's any different.
I also want to second what Jonah had said. I think, of course, this is, Chuck, this is one of the questions we really would like to know. How long is that beast alive? And I think if we say the only physics that we consider is GR and the right equation of state, and then I think probably we could get there on a reasonable timescale. But the major question is is really how do you transport away the angular momentum? And then we have all those boxes of worms, like all kind of winds that can carry away angular momentum, viscosity, MRI, all of these things which are not fully under control contribute to exactly this point. So I think this is very closely related to these other long time scale questions, which are very tough to get right.
Chuck, I just commented that it's very sensitive to the high density part of the equation of state, the quark hadron transition, et cetera. There are a lot of papers about that.
Sure.
What the thing that you asked was how can we get a handle on it observationally, and we really need to see the ring down, because it will show up in the ring down the subtleties of the very high density equation of state. So that was what I just wanted to add there.
I'll also say that if you do have a short-lived neutron star, there's a good chance, and this may be something that someone will talk about, but that if you have a magnet, if you can produce a magnetar in these mergers, and this is the one case where you might form a rapidly rotating magnetar, you have a good chance of producing electromagnetic signals that they're developing. There's lots of X-ray satellite proposals out there to try to see that early time magnetar, not just try to observe the magnetar through secondary photons. So I think there is I think a lot of excitement on the observer end to see, can they see evidence for a short-lived, highly magnetized neutron star.
Chris, can I hijack this for asking another question? That is.
Yes, sir.
Say, I think we all agree that neutrinos play really a key role for everything that we want to know. And maybe a question to Jonah. Say, if we think on a time scale of maybe a decade or so, is it clear which one is the way to go, how to get neutrino transport better? There are all kind of things like low order moment schemes, Monte Carlo, some relatively sophisticated leakage schemes, which by effective methods get at least the accuracy of moment schemes as well. But of course, in the long term, we would like to have something that we can run dynamically with a simulation for at least a couple of tens of milliseconds and have controllable high accuracy. Do you have a clear idea what the way forward would be there?
I think I have a clear idea what's not the way forward. I don't have a clear idea what the real answer is. So, despite this, despite what I've been doing with Monte Carlo methods, for example, I think it's pretty clear that this is not the path for getting long-term models, because what we really want to be able to do is scan the range of optical depths from the high optical depth range of, say, the hypermassive neutron star to the very low optical depth of the disk. And with Monte Carlo, this is not possible. Monte Carlo gets the disk correct very well, much better, I would say, than say any of the approximate methods. But it is incapable of treating the neutron star with in any kind of reasonable time. You'll get stability issues, and also the cost of running in that highly scattering dominated regime will be much too high.
I do. I mean, you always say this, Jonah, but the issue is the labs actually do use Monte Carlo extensively in the diffusive regime, using these diffusion, discrete diffusion Monte Carlo methods. And I think it's probably something you can develop, but the issue with this is, I mean, neutrinos are a little bit harder than photons in the sense that, some of the effects that Meng-Ru was talking about, neutrino annihilation, if you really want to count it, I think the way it's implemented in your code is it's assuming some isotropy in the neutrino fluxes, or it has some angular assumption in the neutrino fluxes because it was designed for supernova where that's more appropriate. But I'm not sure that, you're going to have to do some work to get it to really do neutrino annihilation accurately on a on a disk.
I don't think those are the main issues with Monte Carlo, actually. I would say that the problem is that DDMC does not work in a relativistic context. This could be solved, but currently it doesn't. And the issue is that it assumes infinite signal speeds. So what we need, if we want to do DDMC in neutron stars, is we need a relativistic formulation of DDMC. So
Yeah,
I think
that's like
that's
saying
a path, but
you need that's like saying you need a relativistic solution for the diffusion equation. I think
yes,
they're
it's exactly
fairly
that.
well yeah,
It's exactly
well,
that.
but then you're saying no transport scheme really works in the diffusion limit if you cannot do relativistic diffusion calculation.
Yeah, so there are ways to do this, of course. And in the continuum limit, or in continuum models, we know how to do this. You play this Israel-Stewart trick where you split out. You basically transform the equations into a hyperbolic system where the solution is the same as the solution to the diffusion equation. You introduce auxiliary equations that fix this. It's not obvious to me how to do this in DDMC, where the diffusion model is kind of this random walk thing. Not to say it's impossible, I just don't know how to do it. I think there's algorithm and methods development that's needed there, which is on a long time scale. But sure, that's true. That's one path. I also would say I'm not comfortable with sort of moments and leakage as a path forward, because I think there's, at least in the disk, there's pretty strong evidence that they don't really get us where we need to go. So what I would like to see is hybrid methods where you span from regimes where things work, where you span from appropriate approximations in the regimes where they're valid, and in the middle you do something real. So for example, you might imagine a scheme. So Francois Foucault, I mentioned yesterday, has this moment scheme that's closed by Monte Carlo. So you can do Monte Carlo where it matters, and you can do diffusion where it matters, or where it doesn't matter. And you can even switch to something like free streaming or pooling or leakage in the regimes where you don't need to do Monte Carlo. So this is really where I think I would like to go. And this is where, at least what we're pursuing in our group, Josh Dolan, Ben Ryan, and I are pursuing using Ben's mock-MC method, which is such a hybrid method that kind of spans these scales. And a great way to do this is by evolving a moment scheme, but rather than using an analytic closure, you control the closure. You close possibly by real transport when it's appropriate, and you close by the appropriate analytic closure when you can get away with it.
Zach, is your hand? Oh, Mengro, do you want to talk?
Yeah, so I want to ask another question. So yesterday we heard from Oleg saying that the morphology of the ejecta can make a huge difference for, say, modeling the kilonova light curves, right? So what he answered yesterday was most likely we could probably only get this information from simulations. So I'm wondering, like, how far away or how do we are in terms of the prediction of this morphology of ejecta in terms of the time scale that relevant for kilonovae.
I think getting the morphology is actually easier than getting, well, assuming you can trust the output from, say, my code or a binary, like an in-spiral code, and you get ejecta, then you can, no one has done it yet, but I think it's not unreasonable to try and propagate that inexpensively into the morphology of the ejecta for a light curve calculation. But you have to, there's the implicit assumption there that you trust the output from, say, a disk code, which I don't know how much you should, given that the time scales that disk codes can run is probably too short.
Maybe if I can also quickly answer to that. Say, Mengri, Ru, if I don't know whether you have heard my talk yesterday, but part of the motivation behind doing a Lagrangian full GR code is exactly this. And as Jonas said, it's not yet done, but I think this is stuff that is doable in the next few years. And I think it will be harder to get convergence on these long time scale secular ejector things than just evolving the ejector for a long time in a 3D geometry. So I think in the next 5 years this can be done, but I think it hasn't been done yet.
Yeah, the thing that concerns me with getting the morphology all right is the initial, tidal ejecta. I expect you to get a good solution to, and you be happy with it and tell me, I trust it, Chris, you can believe this. But then as you start to do the subsequent evolution, and especially the disk outflows, things like, running it long enough that you know what's falling back and what's not falling back and all of that kind of, those kinds of effects seem like that's really hard. And I'm hoping someone says, no, Chris, it's easier than you think. We can do the tricks, this trick and this trick and solve this. But right now it seems like that's really hard to me.
Okay, can I maybe just pick up there and sorry, just throw the ball again to Jona. Say, do you think, since you're doing these long-term simulations, do you think your simulations are entirely dominated by physics and not by numerics? If you have these very long time scales, are the dissipative processes that you create by physics, are they clearly dominant compared to the ones that you create by finite resolution numerics?
Yeah, this is a really, really good question. So we have measures of this, but I won't say that we're resolved, so to speak. We're running at the highest resolution we can get away with, but I would not say that we've reached the point where if you did a convergence test, you could confidently claim that things are truly converged. So what we do to try and measure whether or not we can trust the physics is at every time you can ask, well, how many grid points do we have per relevant piece of physics, right? So there's a quality measure that you can do for the MRI where you ask, how many grid points do I have per MRI, fastest growing MRI mode wavelength? And similarly, you can ask the same question for radiative physics, although the radiative physics doesn't really produce any dissipation. By radiative, I mean neutrinos, of course. And the good news is that the resolution requirements are highest early, because as the disk diffuses and cools, the MRI becomes less active, and so the wavelengths lengthen. The bad news is that early in the simulation, when things really matter, we are, I would say, as resolved as the standard in the community, but I would not claim that the community standard is good enough. So it's not a very satisfying answer. I would not make strong claims here, but I would say that we're worried about it.
Yeah, so maybe another question. Yeah, just maybe another question that I remember that I haven't seen many works in the past few years was, for example, once again, for the long-term evolution of the ejecta, or the property of the long-term evolution of ejecta, how much does, for example, a jet or a jet cocoon system would act on or will affect this property? So there were a couple of works in the past few years, but I don't recall seeing very conclusive answers on that.
Yeah, maybe I can. We had recently had a quick look at that, but there are many other groups, and if any one of the other groups is there, please also speak ahead. So we had just looked at, we had taken the neutrino-driven winds that Albino Perego had produced a couple of years ago, And we had just asked the question, what happens if we put in a three-dimensional jet, relativistic jet? How does that affect the outcome? And one thing that we had, I think, probably overlooked initially was that in these simulations, there is a very low YE thin outer layer on those winds. And we had thought about whether this is real or not. And we think this may well be real. And this is like this lanthonide curtain that Oleg had mentioned yesterday. And it's only a tiny fraction of the mass. I think in our case, it was a few times 10 to the -4, but it was still solar masses, but it was still pretty efficient in blocking light getting out of that. And the jet is then just punching away this skin and this kind of just opening, just opening up a funnel so that the radiation can escape. And we found that it would make the resulting transient bluer. But I think there's lots of open issues, and I don't think it's also a self-consistent simulation. It's just put two different simulations produced by two different codes together. And I think at the moment that's the best, at least, that we could do. And I think there may be interesting effects of that, but I think this has just being started to be explored.
This was an excellent discussion. I think we have a pretty heavy slate of talks today. So in order to keep on time, I think we should probably start moving over to the talks for the day. Thank you everyone for the discussion we had. I was hoping this would work out well, and it seemed like it did. We had a lot of good questions. Joey, do you want to start sharing your screen?
So good evening, good afternoon, and good morning to everybody. And I'd like to thank the organizers for inviting me to give a presentation. I've found this meeting so far fascinating, and I think I'm one of the very few experimentalists who've been invited. So I'll be talking about informing neutron capture with surrogate reaction experiments with a focus on systems that could be important for understanding R process and weak R process nucleosynthesis. The measurements I'm going to be talking about today are a collaboration of, first of all, I need to recognize my current and former students and my colleagues from Oak Ridge, Livermore, and of course, Rutgers University. So the work I'm reporting about, some of it is absolutely hot off the press, but also required our detector collaborations, Aruba and Goddess. So this is something that is quite familiar to you. So these are the R process abundances, the solar R process abundances with the first peak, the second peak, and the third peak. In the end, these are the ashes from the events that we're looking at. So the goal is to try to understand these abundances. You require nuclear data to be able to understand these, in particular masses, beta decay, and beta delayed neutron probabilities. But you also need nuclear structure and neutron capture rates, which can be informed by measuring reactions, as well as you need theoretical input. So Matt Mompower, Rebecca Sermon, Gail McLaughlin, and Ani Abrahamian several years ago actually calculated the nuclei where unknown neutron capture rates could have a large impact on predicting these R process abundances that are observed. And in particular, they focused around this second peak. So these are the darker greens are a measure of higher sensitivity. So the understanding these rates are more important. And in particular, they're very important around neutron number 50, neutron number 82, and proton number 50. So these are actually the sensitivities in the Mompower review paper. And what you'll see is the tin 130 is actually the largest for the tin isotopes. But in this case, when you're very close to a shell closure, neutron shell closure, the neutron capture is going to be dominated by a direct process where the neutron is directly populating particular excitations. And so it depends upon the specific properties of low spin bound states. And so you can inform this by measuring neutron transfer reactions with neutron-rich radioactive beams. So the way we do our measurements, we have a radioactive beam, for example, tin-132, which lives for about 40 seconds. It impinges on a thin target. You can think of this as deuterated saran wrap. The heavy beam-like particles move forward in the laboratory system to a recoil detector, and the protons of interest come out predominantly at back angles in the laboratory. And so we do have challenges with having good excitation energy or Q value resolution. While these are difficult to produce, any beam that you can make, we can do the measurement. So many years ago, we did our first measurement was we took a tin-132 beam on a deuterated polyethylene target. And so this is a Q value spectrum. So excitation energy goes from right to left. We identified 5 states with this likely configuration. And in particular, we measured the spectroscopic properties of these states, the spectroscopic factor, by relating the measured cross-sections to the cross-sections calculated theoretically. And in particular, it's the P3 halves and the P1 half states, which are most important in direct neutron capture. So we, in collaboration with Goran Urbanis at Oak Ridge, we've done extensive now semi-direct direct capture with the Cupido code, in which the neutron channel is a Koenig-de la Roche potential, the bound state is a Baer-Hodgkin potential, and we have both direct capture and semi-direct capture, which goes via the giant dipole resonance. What's important is we're using our measured spectroscopic factors and excitation energies to constrain these calculations. And therefore, this is an example of the cross-section for the direct semi-direct capture on tin-130. Remember, that was a nucleus very important from the Munn-Power et al. Study. And what you'll see is that the astrophysical energies on the order of tens to about 100 kilovolts, the cross-sections are on the order of 100 microbarns, but are dominated again by the P3 halves and P1 half capture. We've now measured these on all of the tin isotopes from the stable 124 to 132 dP beams, tin beams. And as you can see, at 30 kilovolts, which is one of the relevant energies, again, these cross sections are small, but we have measured them. So this now summarizes our cross sections as a function of mass number for the tin nuclei. These are our data points. Many years ago, Tommy Rascher calculated from his shell model calculations what it should be for tin-132. So tin-132 was well predicted before we measured it. The red points were calculated by Chiba and Company many years ago before any of these measurements were done. And in particular, they assumed that we had pure spectroscopic strength in the states, which is not the case. But what you'll see is that while for the heaviest tin isotopes above tin-132, the capture cross-section is predicted to be dominated by direct capture, as we go below tin-132, and in particular for the very important nucleus tin-130, the compound, the neutron capture could proceed via a compound process. And so it's when you're below the neutron closed shell, the statistical N-gamma process dominates the cross-section. So while at shell closures, you're going to have direct processes, away from shell closures, you're going to be populating a nucleus at fairly high excitation energies. It's going to decay by many paths down to the ground state. And so the goal is to try to understand this competition between direct capture and compound capture, in particular for nuclei away from neutron closed shells. So the compound neutron capture process is modeled in a Hauser-Feshbach formalism. So again, we populate the compound nucleus. It decays by many paths. So this is the population of the compound nucleus. A compound nucleus is an equilibrated system, and so it forgets how it was formed, and so the decay is independent of the formation. You calculate the neutron capture cross-section by measuring the decay as a function of excitation energy and spin and parity, the formation of the compound nucleus in the neutron plus A system, and you sum over all J and pi to get the total cross-section. The concept of a surrogate reaction, and in this case, we're focusing on the DP reaction, is that you form the same compound nucleus, and therefore it's an equilibrated system. And so the decay of this compound system is the same as it would be for the surrogate. The main difference is that the angular momentum distribution populated in the surrogate is not the same as the direct reaction. And so what we measure is we're going to measure the proton gamma probabilities as a function of excitation energy for specific discrete transitions. We need to calculate that formation of the compound nucleus. And by fitting these data with the formation probabilities, we can deduce the decay of the compound nucleus. The neutron transfer DP reaction is actually a good candidate for surrogate neutron capture with radioactive beams. With the deuteron, we bring in relatively little angular momentum. The reaction is actually dominated by one-step transfer of a neutron with orbital angular momentum L plus or minus a half. It's relatively easy to produce the targets. And the kinematics actually favor a cleaner reaction. So this is a simulation of the energy of the protons as a function of laboratory angle. And at the back angles, the only thing we see are the protons from the DP reaction. At more forward angles, we see other reaction channels, and in particular, elastic scattering on deuterons and protons. There's always a few protons in the target. And so this can help us normalize our cross-sections. So again, what we're going to measure are these proton gamma coincidences, but we need to understand how do we form a compound nucleus in the DP reaction. So Gregory Patel has modeled this as a two-step process in which the weakly bound deuteron breaks up into a neutron plus a proton. The neutron then propagates. We can actually have elastic breakup in which the neutron just flies off, or we can have non-elastic breakup in which the neutron with the target form a compound nucleus. So in addition to predicting the elastic breakup versus the non-elastic breakup, he's also able to calculate the spin and parity of the final compound nucleus as a function of excitation energy. So what we do is you have to measure these proton gamma coincidences. We need theory to calculate the formation probability, and we deduce the decay probabilities by fitting the data with the weighting of this formation probability. We validated this process with a reaction in which we knew what the answer was with molybdenum-95 targets and deuteron beams. So these are our data, the proton gamma probabilities as a function of excitation energy. For various discrete gamma rays, this is actually the 2 to 0 in the final nucleus and other transitions within the nucleus. What's very important is to have this entry spin distribution. So this is now the entry spin distribution for a region near the neutron separation energy. And the first thing you should notice is that at these low energies above the neutron separation energy, you cannot assume that the parity distributions are the same. What you see is that the negative parity states are about an order of magnitude more strongly populated than the positive parity states. The other is that the most likely states to be populated in the DP reaction have angular momentum 3- and 4-, while an L = 0 neutron would populate 2+ and 3+ states. Finally, Jutta Escher has been doing our Hartree-Fock calculations, in which she uses a Bayesian fit to reproduce our data. She uses a level density of Gelbert and Cameron, in which she does not have to normalize to the unknown in a rare isotope, L = 0 resonances at low energy. And also she doesn't have to normalize, she doesn't need to know what the average gamma ray strength is. You just use a modified Lorentzian for gamma ray strength. And so by taking our data, the entry spin distributions from Gregory Patel, she's able to calculate this complicated gamma decay probability as a function of excitation energy, angular momentum, and parity. That is the ingredient we need to calculate the cross sections for neutron capture. And what's important here is that we also need to understand the formation of the compound nucleus with real neutrons, and that's done with Koenig-de la-Rose optical potentials. So these are now the results. Excellent fits to our data. And by taking the decay probabilities that were deduced from our data and putting them into the calculation, Hauser-Feshbach calculation of the cross sections, we're able to show that, so these are the results. They reproduce the data, and they reproduce actually quite well the NDEF evaluation for this cross section. If we had not assumed that, if we'd assumed that the population in DP was independent of spin and parity, that's this Weisskopf-Ewing limit, you see that we actually are off by an order of magnitude or more. And so I feel that we have validated the DP gamma reaction as a surrogate for neutron capture, and therefore are ready to do measurements with radioactive beams. So just to summarize what we've done so far, I wanted to emphasize that we need, first of all, to measure these reaction rates because they're important to understand our process abundances. We can inform the direct capture components of these rates by measuring the DP reaction with rare isotope beams. And we have validated a compound nuclear reaction to populate a surrogate for neutron capture, where we had to take into account the differences between entry spin parities between the compound nucleus formed in the DP and with real neutrons. So the other thing we need are the experimental techniques, both to inform the direct capture and to inform the compound nuclear capture. And so the way we've been doing this is that we couple our charged particle detector array called Aruba to state-of-the-art gamma ray detectors. And this is actually what it looks like when it is coupled to Gratina, which is the state-of-the-art gamma ray tracking array in the United States. The frame is now open. It would be closed to do the actual measurements. We've completed measurements at Argonne National Laboratory in 2019, and I'll be reporting on data we completed on July 2nd. I'm going to be focusing on measurements we've done with rare isotope mass 180 neutron number 50 beams. So these are the ones in the first peak, which are important for our isotope for weak R process nucleosynthesis. And that's mainly because these beams are readily available and amenable to doing our measurements. So Rebecca Sherman and a company many years ago actually did a sensitivity study to determine which neutron capture rates were most important for understanding weak R process nucleosynthesis. Many of these are around neutron number 50, And it's in this region in particular where we expect to have competition between this direct and compound nucleus capture measurements. So we completed a measurement with selenium-82 beam. Selenium-82 is stable, but is actually between two nuclei which have finite sensitivities to trying to reproduce weak R process abundances. But actually the neutron capture on selenium-82 is actually not well known. First of all, it is very small, which means that it's dominated by direct processes, but the evaluations, NDEF and GENDL, differ by about 2 orders of magnitude, and there's essentially no data. There's only limited data around 1 MeV. So this is really hot off the press. This particular plot I received at about 6 o'clock this morning. This is a plot of counts as a function of excitation energy in selenium-83. What's very important is that we're clearly seeing transfer to states. There's a doublet of states, a 1/2 plus and 5/2 plus state at about 550 kilovolts. This peak is actually probably dominated by the 1/2 plus, and that's actually what's very important for P wave capture. In addition, we can gate on our particle data and look at gamma ray spectra. And we are, first of all, seeing gamma ray transitions in selenium-83. And very interestingly, we're actually seeing gamma rays in selenium-82. Now, these are in the upstream detectors where we should only see DP. But if you go to very high excitation energies in, so in this, not ignore the contaminant, but if you're like at these very high excitation energies above the neutron separation energy, you've got a lot of cross section. And so you're populating states above the neutron separation energy that decay by emitting a neutron. And so you can think of these as being surrogate and primary actions. So we're clearly seeing gamma rays above the neutron separation, populating states above the neutron separation energy. And so we're looking forward to showing more of these results in the future. So this would be the first example of a nucleus where we're going to study both the direct capture and the compound nucleus capture in the same surrogate reaction. In addition, Gregory Patel has calculated the entry spin distributions, and you can see that near the neutron separation energy, we're dominated by L=3 transfer, and there's also only as we go up higher in excitation energy do we see a lot of non-elastic breakup, which needs to also be subtracted when we determine the probabilities for proton gamma coincidences. Our next step is actually to measure with a germanium-80 beam, and this actually has quite high sensitivity in understanding weak R process nucleosynthesis. This reaction has actually been measured at a lower energy, so we're going to be able to better constrain the direct capture on this nucleus. But very importantly, this has been approved to be measured at FRIB, which we hope will take place in early 2022. To do this, we had to do some work on our detector system. So first of all, we needed a smaller target chamber because right now we can't fully close Gratina. We've also have some upstream gas tracking detectors, and we've also developed some upstream detectors which have a smaller footprint. So please stay tuned to our measurements in germanium-82, which would be a measurement of the competition between direct and compound nuclear capture on a nucleus important for the weak R process. So to summarize, I feel that you probably all of you realize that understanding the abundances from neutron star binary mergers and weak R process nucleosynthesis is sensitive to the neutron capture rates, and in particular near closed shells. We're looking at tin-130, which we've measured the direct capture for, and germanium-80. Where we're hoping to measure both, constrain the direct capture, but also the compound nuclear capture, and that competition between the two in weakly bound nuclei, which have relatively low density. And we have all of the experimental tools in place to actually measure the DP protons in coincidence with gamma rays to understand this competition between direct and compound nuclear capture. First of all, we have data now with stable selenium-82, and hopefully a year from now, we'll have data on germanium-80. And so I'd like to thank you for your attention.
Billy, thank you so much for a great review. It's just amazing the work that you guys are doing with this, getting to these isotopes that we really need to do to understand to do our process. It looks like we have a question from Carlos. Carlos, do you want to ask your question?
Yeah, can you hear me?
Yeah.
Yes, we can.
Hey, Jolie, it was a very nice talk, and congratulations for wonderful results. I have a question about the benchmark you have done with molybdenum, and so you have shown there some error bars in that comparison you have. The other one, the previous one, please. Yeah, that one.
This one?
So what are these error bars? So the
Okay, so these are statistical. So let me see if I can pull up something. This is what I want. Okay. So when you populate I don't know, I can't see my camera right now. So when you populate a nucleus at high excitation energy, it cascades down in many different paths. And so this 2 to 0 transition is basically collects all of the strength. And so these error bars on our data are from are basically statistical uncertainties in determining it's dominated by the intensity of the gamma ray transition.
So you do not have systematic uncertainties like coming from the calculations that...
So the data points are pure data.
Okay.
Okay, so any systematical uncertainties from our experimental setup are included in these data points. And the transitions which have larger uncertainties are, for example, the 6 to 4 transition, and most of the feeding goes directly to that ground state, and so therefore we have much less intensity here. But I think where you were concerned was, and we were actually quite impressed, is this, so what if, I don't know if you can see it, the central line, so the results are the blue.
Yep.
Okay, so the central line is the result, and now we have an uncertainty error bar. And Jutta Escher did slight changes in what the level density could be, but she did a Bayesian fit, so she has uncertainties from that. And then Gregory Patel used slightly different optical model potentials and to see what's the difference in his spin parity entry distributions from the DP reaction. So this actually includes the uncertainties in the theory, as well as the uncertainties in the data.
Great. May I have one more question? So do you have any other benchmark you could do with other nucleus? Because this is so beautiful, it works so well for this case, but would it be, because this would strengthen your hypothesis that you can really do this with the surrogate reactions, right?
Okay, see if I can pull it up.
Are you planning to do some?
I'm just trying to find the, is that our selenium? Yes. So actually the data we have is a stable nucleus.
Okay.
Okay, so we can compare it. So we've measured now the selenium-82 DP gamma. And we can actually determine, we should be able to determine which of these, I assume these are large enough. We can see whether or not the NDEF, I think this is the NDEF and these are the Gendel evaluations are correct. There are some limited data here. And and there's actually now some preliminary real neutron capture on this nucleus from Dance at Los Alamos. And so this measurement will be another, can be also considered to be another benchmark as well as constraining which of these evaluations is correct. Because I think that when we were proposing this measurement several months ago, we were actually surprised that the evaluations disagreed with each other so dramatically for this nucleus. The challenge in doing the real measurements is that it's really dominated by direct capture. So these cross sections are tiny. These are on the order of, well, they're basically microbarns.
Microbarns, okay.
Yeah, so
Thank you so much.
it's tough to do real measurements. Thank you for your
so much.
questions.
Thank you.
So Joey,
I have a quick question on just the mechanism itself. So you basically do these measurements, you then have some model for the gamma strength function, and then you're determining that other component. My question is, for nuclei like germanium-80, one of the things we noticed is that with our systematics is we predict a really large M2 enhancement. I'm sorry, M1 enhancement for the capture cross section, which really impacts the Hauser-Feshbach part. So the compound nucleus formation. Is that something that you guys can take into account?
So, so in the case of basically all of these nuclei near n = 50, the direct capture either goes by P wave capture plus E1. I don't know if you put in the P wave capture, or S wave capture and M2 and M1. So so your capture is low near the neutron separation energy because one, it's dominated by direct capture because they're close to a closed shell, but the other is that we see that it's actually P wave. We've done other calculations in this mass region. In particular, we've done the direct capture calculations on germanium-82, selenium-84, and germanium-80 based from low energy data. And we also have now done it for selenium-84 based on high energy data. So it's really dominated. So you can either say it's M1 enhancement or it's P wave capture. So you have two processes. The other one is that the way I understand that Yuta's calculations work is that she doesn't determine what the parameters are in her level density and strength function. So she does, for example, a lot of people think you need an E1 enhancement at low energies. She doesn't include that, and actually finds that from the limited work we've done so far with her, that she doesn't need that E1 enhancement. So it'll be interesting to see when we actually start analyzing the selenium-82 data sets. I've been amazed at how quickly I've been able to get any preliminary results out. My collaborators, Student and Steve Payne, have been working extra hard to get something out. And I'm glad I was able to show something today. So I ask you to stay tuned, and we'll work with you as we're trying to interpret our results.
Yeah, that's really fascinating. Thanks.
Thank you.
Thanks again, Joey. Our next talk is by Sabrina Hussa, and she's going to talk about, we're going to switch over to constraints on nuclear equations of state.
Yeah, thank you.
And Sabrina, I'll give you a 2-minute warning.
Okay, thanks.
So at 18 minutes, I'll give you a warning.
Okay. Yeah, first of all, let me thank the organizers. I'm very happy to present here the work I've been done over the last couple of years with my collaborators and to share this with the community here. So we already heard a couple of times that the equation of state is a key microphysics input, and this as well in core collapse supernova simulations and also in neutron star merger simulations, of course. And what I've worked on is to generate equations of state for these simulations that are consistent with what we know of right now from nuclear physics and also from observations. So for this talk, I will present basically two projects. The first one is where we generated a new equation of state functional that can be used in the simulations. And in the second part, I will also show you very recent results to constrain the equation of state using heavy ion collisions, which will be actually submitted to arXiv today, so you can find this then tomorrow. Okay, so when we start making new equations of state, then we usually look at nuclear theory up to or around saturation density. And there you can expand the energy per particle at saturation density, which I show here as the energy per particle as a function of density. And for symmetric nuclear matter, you have this saturation point for the density and the binding energy. And the incompressibility gives you the second derivative around the saturation density. And then for neutron matter, for pure neutron matter, the important parameters are here the symmetry energy. So this is just the energy difference from pure neutron matter up here to symmetric nuclear matter. And then the slope parameter here also gives you basically the slope of pure neutron matter, which is very important for neutron stars because it correlates with the pressure. And so when you look at nuclear theory, then here in this table, you see some estimates for all of these nuclear matter properties, and also here for the effective mass at saturation density. And I won't go into detail here about this table. The important thing is just that if you look at equations of state for finite temperature that are usually used in simulations, like here the Latimer-West T220 or also the Shen AOS, then you see that those are not for all parameters consistent with what we know from nuclear theory, especially here for the slope parameter. So what I did with Corbinian, Wellenhofer, and Achim Schwenk was to construct a new energy density functional that of course depends on now on density, proton fraction, and also temperature, where we can include all the constraints we have so far. So you see here this functional for the energy, and the first term is basically just the kinetic energy density, where also the effective mass enters. And then we have these potential terms, where this delta I here gives you basically the density dependence of your functional. And for this, we used two different sets. So the first one, if you plug in these numbers, then you have basically a KFA expansion. And for the second one, you have really an expansion in powers of densities. And for each of these expansion coefficients, we also choose the steep parameter, which then ensures a good fit performance over a wide range of fit parameters. And what's really novel here is that we also have the density dependence here in the denominator, because we found that this really ensures a stable interpolation between low and high densities. Then we also have 8 fit parameters, these AIs and BIs. And these are used to constrain the equation of state. So we, first of all, fit those parameters to nuclear matter properties, so which I have shown you before, and also to the energy of neutron matter at very low densities, which we have from precise quantum Monte Carlo calculations. And then we have 2 more fit parameters left, which we use to pin down the pressure of pure neutron matter and symmetric nuclear matter at 8 times saturation densities. So this is really at high density, and with this we can, if we vary these fit parameters, we can actually cover the whole range we have from astrophysical observations. Okay, so let me dive a little bit deeper into the nuclear physics constraints that we use here. First of all, you see here the energy per neutron as a function of density from chiral effective field theory calculations for pure neutron matter. And you see that all of them are pretty consistent with each other. And now with our equation of state functional, we want to basically cover this whole theoretical uncertainty range. And for this, we use 4 different pairs for the symmetry energy and the slope parameter, which you can see here in this correlation plot on the right. So the bands are basically the same theoretical calculations that you also see in the left picture. And then these 4 green dots are the pairs of symmetry energy and slope parameter that we use for our functional. And when we use those, and also for symmetric nuclear matter arranged for incompressibility and the empirical saturation point, then we can actually cover this whole uncertainty range, theoretical uncertainty range for pure neutron matter here on the left. And we also use the unitary gas, which you see here as the dashed dotted line for a lower bound for the energy of pure neutron matter. Then another very important constraint for us comes from the nucleon effect of mass. And in a previous study, we found that the effect of mass governs the proton-neutron star contraction in CocoLab supernova simulations. This is a project I've done with Hannah, Yassin, Almudena, and Achim, and Almudena already showed you this figure yesterday. So you see the proton-neutron star contraction here on the left and the shock evolution on the right. And basically what we did was we used the Latimer-Svesti 220 EOS, which you see here in blue. And then we only changed the nucleon effect of mass, but all other parameters are the same. And we found that if we include the effect of mass value that is used at saturation density for the Shen EOS, then we end up with this pinkish line here. And this gives us basically the same radius of the proton-neutron star in the simulation than the original Shen EOS. So this really showed us that the effect of mass determines the proton-neutron star contraction, and this is done through thermal effects, which are also, of course, important for neutron star merger simulations. So for us, it's now very important to implement accurately the effect of mass in our new equation of state functional. And for this, we use recent results from chiral EFT calculations at finite temperature from Ariana Carbone. You see this here in this plot for the effect of mass as a function of density, in red for symmetric nuclear matter and in blue for pure neutron matter. And with chiral EFT calculations, we can here go up to twice saturation density. So right now, unfortunately, we don't know what the effect of mass is actually doing at higher densities. So we came up with a parameterization for the effect of mass that is very flexible here in this high density range, so that we can cover also there quite a broad area. And what's now really key here in this description is that usually, if you look at finite temperature equations of state for simulations that also include an effect of mass, then there the effect of mass only decreases with density. And here you see this turnover behavior at around saturation density, which is due to 3 nucleon forces. And this now has really a significant impact on the thermal index, which is of course very important also in simulations. So for example, in many or in some simulations also for neutron star merger, often a constant value of the thermal index is used. But we found here when you use this, or Ariana found this, and also this is done by Jonas Keller, is confirmed by Jonas Keller and collaborators, that this might not be a good approximation for the thermal index. Okay, and then if we include all of these constraints and parameterizations in our equation of state functional, we have still these 2 fit points at very high densities, which we use to cover the 2 sigma bands from a joint analysis of Reimarkers et al. So these are our observational constraints that we use. And in this joint analysis, they include the measurement of a heavy neutron star, the measurement from gravitational waves, and also the first NICER results. And this is depicted here in this gray band for the pressure as a function of density. And then these green bands come from our equation of state functional when we vary all fit parameters in the ranges that cover also nuclear theory uncertainties, and then of course the uncertainties here from the observations at high densities. And you can see that with our functional we can actually span almost the entire band here from Reimarkers et al. And then I also show you the results for the speed of sound as a function of density. And you see that the band up to 1.4 solar masses, where you have this dark green color, is still pretty narrow. But then if you go to heavier neutron stars, so higher central densities, then this band becomes pretty broad. And even when you extend this, then in this gray area here to even higher densities, which are of course above the stable central density of neutron stars, then we can cover a range from 0.2 to almost the speed of light here. So this is really a very general description for an equation of state functional. Okay, and then let me also show you our results for the mass radius relation. So here you can see the final result for our radius, which is also in good agreement with what has been published by Reimarkers et al. And here for the plots, you see on the left the equation of state, so pressure as a function of energy density, and on the right the mass radius relation. And then we additionally used a constraint for symmetric nuclear matter that is based on quantum chromodynamics by using functional renormalization groups from Mark Leonard and collaborators. And if we include this also in our equation of state, then you see this orange band here. So we just had a look which equation of state is actually consistent with this constraint from the FRG method. And you see that this is quite constraining already for the equation of state. So this constraint is only for symmetric nuclear matter. But of course, it also has an impact on neutron star matter because you build your equation of state on symmetric nuclear matter plus pure neutron matter, of course. So here we have this more softer equation of state at higher densities, and therefore we see the significant impact here on the mass radius relation if we include this constraint in our analysis. And right now we are working on building equation of state tables that can then directly be used in Coriolis supernova and neutron star merger simulations, because of course right now these are a lot of different equation of state here that I show you from our functional, and we will use representative equations of state out of this set and make this then available to the community. And at the end, let me also compare this to heavy ion collision constraints. So here's a plot for the pressure. In blue, you see constraints from chiral EFT, and in orange, the one from this FRG calculation I've showed you before. And here you see that this really starts at 3 times saturation density, and it goes up actually up to 10 times saturation density. So this is really at these intermediate densities that are very important for neutron star mergers, and we are very excited when new constraints also for pure neutron matter might come available. And in green, this is what our functional, the range of our equation of state functional. And then we compare this here to this gray band from Danielewicz et al., which analyzes heavy ion collision experiments. And first of all, you see that there is really a promising consistency between all of them. But at the same time, the heavy ion collision experiments have really the potential to constrain the equation of state at these intermediate densities. And this is then what I want to talk in the last couple of minutes. So this is a very recent project on constraining the equation of state with these heavy ion collision experiments. Here we actually use, so this is now not built on the equation of state functional that I showed you before, but rather on a multi-messenger framework. And for heavy ion collision experiments, we used mostly two different experiments that were done at the GSI in Darmstadt. And these give constraints mainly between 1 to 2 times saturation density. So there is this FOPI constraint for symmetric nuclear matter, which gives the result for the incompressibility. And then there is the ASI-EOS experiment, which constrains the symmetry energy. So they have this functional here for the symmetry energy, and then this gamma ASI parameter is fitted to experimental data on the elliptic flow ratio. And here in this plot that I've already showed you before with this various chiral EFT calculations, I added on top the range from these two experiments. So FOPI for symmetric nuclear matter plus the symmetry energy for ASI-EOS. This is here depicted in this red region. And you see that especially at higher densities, that these are very compatible or consistent with the chiral EFT results. But if you look closely, the slope is actually larger here. So this means that it also favors higher pressures. And then there's also this Danielewicz constraint, which I showed you in this pressure plot before, which is sensitive to higher densities. And we basically use this. We use this to constrain the results here for FOPI to make sure that all of this is consistent, and this has also only a minor impact. Okay, then let me show you our results that we obtained for the constraints on the equation of state. So in this first panel A here, this is our prior, which comes from chiral EFT at lower densities, and then a speed of sound extension at higher densities. And then in the first step, we only included multi-messenger constraints. And you see that this has mostly an effect at larger densities, and it's cutting away soft equation of state as well as stiff equation of state. Again, starting from the prior, we also included just the Higgs experiments without any astro data. And you see here in purple, the two lines for the 1 sigma and 2 sigma intervals, the combined ones for these 3 Higgs experiments. And you already see that this favors higher pressures. And therefore, if we combine astro and Higgs experiments in this D panel here, then you see that in this dark blue area, this is really shifted to larger pressures compared to up here. Due to only the Higgs experiments. And this is around saturation density up to 1.5 saturation density mainly. So you can also see this here in this panel E, which is the probability density actually here as a function of the pressure. And when you compare the green astro curve and the orange Higgs only curve, then you see that Higgs favors slightly larger pressures, but at the same time, we really found a remarkable consistency between those two at 1.5 saturation density in this case. So this is now the same plot, but for mass and radius. Here you also see this panel for 1.4 solar mass neutron star. And since the Higgs experiments are mostly sensitive to, let's say, around 1.5 times saturation density, their biggest impact is, of course, at smaller masses. But we still see here a shift in the radius of a 1.4 solar mass neutron star, again, to higher radii. But to make really, so in order to get Higgs experiments to really pin down also the uncertainty range for neutron star mass and radii, we really would need experiments that are sensitive to higher densities and also with a reduced experimental uncertainty. And then this is really a great opportunity to really constrain this intermediate density range where we have not, so where chiral EFT is not applicable anymore, but also Astro is not so sensitive. Okay, this is our multi-messenger framework. Just quickly, we include maximum mass constraints and the recent NICER, so both NICER results and also, of course, everything around the gravitational wave. But if you have any questions about this, you can, of course, also ask me. And with this, I would just leave my summary and thank my collaborators for everything, and thank you for your attention.
Sabrina, thank you for an excellent talk. Questions for Sabrina? Oh, here we are. Willem?
Yeah, just for my clarification and maybe also helpful for other people, the importance of the effective mass is striking. And I want to clarify whether I have to interpret this effective mass as being equivalent to the specific heat of the system. This is what you normally do in a quantum liquid, that you identify the effective mass as being proportional to the specific heat. This is something you do for liquid helium-3, for example. Or should I just think of this effective mass as a parameter that governs the kinetic energy density and doesn't have this additional interpretation?
Yeah, here the effective mass is basically used because usually, I mean, you would use the self energy and everything to govern, to get all the interactions between every nucleon and so on. And this is just, so this description on the microscopic level is then just approximated with the effective mass, where all the interaction effects are basically absorbed into. And why the effective mass is so important here is because it basically determines the thermal contribution to the pressure. And therefore it governs the thermal index and then the whole thermal contribution,
Just a brief comment. Analysis of finite nuclei suggests that near n equals z, the effective mass is essentially equal to 1. So I think there is some tension between what you're using and these kinds of considerations.
Do you know at which density this is?
No, real finite nuclei.
Okay, yeah. Okay, thanks for this comment.
Yeah.
Jürgen, do you want to ask your question?
Yeah, thank you. Thank you for the nice presentation, Sabrina. Actually, I have 2 comments, but I would like to add something also to the previous questions. Well, with Debarati Chatterjee, we just finished recently an analysis in relativistic field theory, also fitting to astrophysical data and nuclear physics data. And we find also that there's an extremely strong dependence on the effective mass, which controls actually in relativistic field theory, the high density behavior of the equation of state. So this is what it does in the relativistic field theory, but this is known already from the 80s or so. The 2 questions I have is about the use of heavy ion data. So we used actually data from chaos, from the chaos experiment, where they set limits on the equation of state around 1 to 2 times saturation density. And this is, of course, some older data, but there was a long discussion why they see a softening of the equation of state in this density range, and which is still compatible or should be compatible with a 2 solar mass star. So I think in your case, you're arguing that the equation of state is somehow stiffer from the other data you're using, but I think the chaos data shows somehow more the other trend, that you have a softening of the symmetric nuclear equation of state around 1 to 2 times saturation density. And the third question I have is, what do you think would be the role of phase transitions? I think you just use a smooth interpolation or extrapolation. What would happen if you have a jump in the speed of sound squared, for example? I think these issues are not explored yet in your analysis, right?
Yeah, so maybe for the first question about chaos, I just know, or in our collaboration, so I also know about these data, and as far as I know, they are compatible with the constraints we have here from FUPI and ASIER, so within the uncertainty ranges. And I just, of course, I don't know how this would affect now if there would be an effect on our analysis, but stiffening, of course, or when I say it prefers higher pressures, then this is, of course, to also, I mean, it's related to something else, right? So here we have this related to astrophysics, for example, or to our prior. So yeah, maybe also there the chaos would also favor stiffer equation of state in our framework, you know?
In our case, it makes the radius a little bit smaller.
Okay.
We include
so
that constraint.
Yeah, that's a good comment. So then we can maybe also have a look at this.
Mm-hmm.
And for the second one, so here in this project, it's actually included. So in our prior, we have so Ingo Teves is doing the prior calculations here, and there he sets up an equation of state, and then also a second equation of state, which includes a phase transition. So here phase transitions are actually included, but as you said in the first, so in my equation of state functional with Corbinian and Achim, so far there are no phase transitions included. But I think this is can be done pretty easily. And then, of course, it would be very interesting how this would have an effect also on our final result for mass and radius.
Mm-hmm. Thank you.
Okay, Sabrina, I'm gonna have Stefan ask his question, but can you stop sharing and we can have Willem set up his talk?
Yeah, just very quickly. First of all, very nice talk. But I was just wondering whether I got this right. When you say thermal index, you're talking about what the thermal contribution in a polytropic equation of state.
Exactly. Yeah.
So, and is your message just bad? Don't do it, or is there anything better? Say, I fully agree. It's probably not a fantastic idea to just fix this index to some number which is in the right ballpark. But is it possible to make a fit or something which makes this dependent on the physical conditions and therefore potentially better?
Yeah, so in this paper from Ariana and also a recent one from Jonas Keller, they showed that if you use the effective mass, then you can mimic basically, or then you get the real or an accurate description of the thermal index. So without, then you don't need the accurate description of the thermal pressure and thermal energy densities from chiral EFT, but you can just implement this with an accurate description of the effective mass. Yeah.
Okay, thank you. Can you maybe put if you have it just right around, can you maybe put in the citation in the chat or so?
From
this
Ariana?
Keller paper? Yeah, or whoever describes this in some detail.
Okay, yeah, I will do that.
Okay, thanks a lot.
Thank you.
Thanks again, Sabrina. To try to keep on time, we'll move to the next talk. It's Willem Dickoff with neutron skins and equations of state.
Okay, I hope you can hear me, and can you see my slide?
The slide looks good.
Okay, then let's get started. So I also thank the organizers for the opportunity to give you perhaps a slightly different perspective on the story relating data in nuclei to physics of neutron stars. And as the next speaker has clearly shown and propagated, neutron skins that can be cleanly measured have a relevant connection with the physics of neutron stars, and I applaud him for that effort that is now coming to fruition. And in addition, we know that one would like to have these measurements turned into neutron skins and have an impact on the equation of state of neutron matter. I would like to give you a complementary perspective on that, discussing some of the results that we have obtained using what we call the Green's function or propagator method, which can either be used as a vehicle for ab initio calculations. I show you one slide of that. And then as well as a framework that allows you to link data in nuclei, experimental data, at both positive energy and negative energy, which then in turn allow you to make predictions both for exotic nuclei, think of optical potentials relevant for neutron capture, but also for things that can, with great difficulty, be observed, at least for stable nuclei, that is neutron skins. This method is called the dispersive optical model. It was initiated in Belgium by Claude Mahot, and since 2006, we have updated and extended this quite a bit in St. Louis. So we can now give you these types of non-local optical potentials or nucleon self-energies for this range of isotopes that I identify here. I will then briefly review some of the experimental data that have been generated with a proton knockout reaction induced by electrons that identifies in the cleanest possible way how correlated nucleons are near the Fermi energy. And there is an important n-z dependence that people would like to understand. So I'll give a brief update on that before discussing our predictions for neutron skins in 48 calcium and lead toroid. And then I will hopefully make some comments, have time for some comments, which not criticize, but at least try to make you aware of the fact that many of the links that have been used to link finite nuclear data to infinite neutron matter have been confined in the paradigm of density functional theory. And I want to clarify that not everything you learn from that necessarily survives if you go beyond mean field theory. So then I will try to conclude with an update on perhaps a question to ask about nuclear saturation properties, which have always been written in stone, but we may have to go back to that and try to improve our understanding a little bit. Okay, so let's go briefly to identify the people involved. A lot of experimentalists. I am, of course, a theorist, happy to discuss experimental data, as I have for a long time. There are experimentalists involved, these senior people, two of them in St. Louis, two retired people from NICHF, and experimentalist who is now at Livermore, and several of my graduate students and also undergraduate students at Washington University. Some reviews are identified here related to the dispersive optical model, as well as the general features of the optical model and the quenching of the single particle strength that I briefly attend to recently published here. So let's okay, perhaps before I go on, if you wonder what this is, it has to do with the Compton effect, and maybe you realize that Compton did his experiment at Washington University almost 100 years ago. In fact, next year it will be 100 years ago. So the photon, as it were, was discovered in St. Louis. Didn't know that, perhaps. Anyway, this is the general framework, the propagator method. I want to briefly identify what it contains. It contains the possibility of adding to the ground state of the system a nucleon, which can then propagate in the system with one particle more before returning possibly with different quantum numbers to that ground state. So that's one aspect. This particle part of the propagator clearly has links to the possibility of describing elastic scattering of a nucleus. The second part of this propagator contains the removal amplitude, it identified here, and then propagation in the system with one particle less. This object, this whole part of the propagator can give you information on any one-body expectation value of the ground state. It can also give you information on the energy of the ground state, and it tells you directly information on removal probabilities, spectroscopic factors that have been mentioned in the first talk today. Typical useful quantities are the spectral function identified by the imaginary part of this object, identified by this expression. So removal probability chosen here to be represented in momentum space, but you can use any space. And this is, of course, for energies for removal. And if you have a discrete transition, you identify the normalization with this spectroscopic factors. You can do many other things with that. And as I said, the particle part is associated with elastic scattering. This information is used. Some of this stuff can be found in textbooks, one of which I have co-authored. So in case you're interested, there is more information in books on this subject. It leads this propagator to an analysis in which you obtain this propagator from what we call the nucleon self-energy through this box, this Dyson equation. This can be manipulated into a Schrödinger-like equation, which gives rise to these amplitudes for removal and spectroscopic factors. It also yields these distorted wave scattering functions. One thing I should mention here at this point is that whatever Hamiltonian you have chosen, two-body, three-body, anything that you have available, it can be formally reintroduced in this format. And we're not going to analyze data using some chosen Hamiltonian, but we're going to assume that there is such a Hamiltonian which will lead to a self-energy, and we are going to parameterize this self-energy and constrain it by data. We're doing that in a particular way. We use this link between the particle part and the removal part using dispersion relations. This means this is a causal approach. And it also leads to a possible extension of the standard analysis of optical potentials because this self-energy is necessarily non-local. And for purposes of ground state information, this is essential. I will not emphasize that, I'll just mention it here. So with this in mind, let me briefly mention also that this method can be used for ab initio calculations, for example, by solving the ladder diagrams in matter, doing this self-consistently. Current expert on this subject is Arnau Rios. Unfortunately, one of our collaborators last year suddenly passed away, and I want to dedicate to his memory all the good things that he contributed to a long-standing collaboration. I think we have together 38 papers published, so it's a sorry moment when he passed away last year. Anyway, the kinds of things that I wanted to identify here is that these kinds of calculations are available, can generate and will generate equations of state as a function of temperature for a given and an interaction. I'm showing here some results for the argon V18, and they can give you information as a function of nucleon asymmetry, the usual definition, as well as chosen realistic nucleon-nucleon interaction. It shows you here momentum distributions the difference in momentum distributions between protons and neutrons in the interior as a function of asymmetry, which apparently is essentially dictated by nucleon-nucleon data. Note that this is done for 5 MeV temperature. It can be done for any temperature, and it's relatively easy for higher temperature. So I just want this community to be aware of that. It is available for your usage if you so desire. Okay, so back to the dispersive optical model as we have implemented it. We're doing that since about 15 years. As I said, you use experimental data to constrain the nucleon self-energy while doing this link between structure and reactions using dispersion relations actually in a subtracted form. I'm not going to go through the process of how this is done and what kind of assumptions are going in there. Typically, they're rather standard. And we don't make any exotic assumptions, but the result of such a fit then is identified by the figures you see in this slide. It includes in this domain all elastic scattering data of either protons or neutrons on lead-208, including polarization data, including reaction cross-sections for protons and total cross-sections for neutrons. And you see it's possible to fit these data accurately. While you do that, it has implications for what happens below the Fermi energy. So you have to do that simultaneously. And data below the Fermi energy, in fact, E less than 0 is just a similar identification. Allow you, unless, of course, you go back to local potentials, but once you go to non-local potentials, both for the real and imaginary part of the self-energy, it allows you to describe elastic electron scattering data, which, of course, as you well know, will give you the nuclear charge density of lead, and there's both an experimental band here, purplish, violet, and the DOM result. So this is a highly accurate representation of the charge density and confirmed by this very accurate representation of the experimental data. So this type of analysis gives you, therefore, a complete one-body picture of the nucleus and gives you some information on the ground state. It, of course, also gives you distorted waves, which means that together with overlap functions and spectroscopic factors, you can check whether what you have fitted here is consistent with one of the most important knockout experiments that have been measured in nuclear physics. And that's what this plot illustrates. These are calcium-40 and calcium-48 EE prime P data, which we recalculated using only our DOM ingredients. And we found that with the corresponding spectroscopic factors identified here, I didn't put it here, it's slightly less, for this D3 removal, proton removal. You see the cross-section is accurately represented, but this spectroscopic factor, the normalization, was not adjusted. It just came from fitting the other data. And then if you recalculate the distorted wave impulse approximation cross-section for this reaction, you get accurate results. You can then turn this result into a spectral distribution where the 0.7 strength of the D3 is identified by this peak for the solid line, and then there is additional strength at more negative energy, and there is some depletion identified by this information, which I should emphasize is dictated by allowing you to fit elastic scattering data in this domain. If you wouldn't fit those data, or if you would do this in a mean field picture, there would be nothing here. There would be no strength and there would be no partial occupation. And in a mean field picture, you would have a spectroscopic factor of 1, which would not be consistent with this analysis. All right, so we do this from 40 to 48, can then give an error band because the original data have errors, and therefore we can refit our data within those errors and generate these DOM results, these four squares. These are consistent with the E prime P data and actually represent the data better than the original NICF analysis. If we extend it very naively to larger, what is called removal, symmetry removal, asymmetry, proton and neutron separation energy differences, and compare that with this plot from Alexandre Gade obtained from nucleon knockout reactions with beryllium targets with rare isotopes, we see that there is a slope. Our slope is perhaps not as large, but we have brazenly extended this slope to larger delta S, both more negative and more positive. It's an indication that at least we can start thinking of extrapolating with our potentials, which then give you optical potentials in these domains as well as these domains that may be useful also for neutron capture calculations in the future. In any case, this is an ongoing story because transfer reactions give you a flatter curve, and proton-induced knockout with proton beams or proton targets in inverse kinematics also are not consistent with this. So this is an ongoing issue in nuclear structure physics. Our current understanding is summarized in this review, which includes all these possible reactions. Okay, so this is my update on this subject. Let's now go to the predictions of neutron skins. As you realize that you can generate the proton distribution and therefore the charge distribution for such nuclei, you can also generate then a prediction for the neutron distribution. It's not constrained by data telling you exactly what that distribution is, but it's constrained by other information, including elastic scattering, to some extent level structure, and of course for calcium-40 isospin symmetry. So we can discuss, and I'll show you some skins for those nuclei as well. This could be a little early, I think. Anyway, the skins for calcium-48 can be extracted from this result, which contains the charge, our description of the charge, the weak charge, and the neutron distribution. Note that the neutron distribution isn't much different from the charge distribution, so it's an F7.5 dominated contribution here. For lead-208 situation, more recently predicted, again, charge, weak charge, and neutron distribution. You see there's a substantial presence of S-wave content as well near the origin. Let's turn this into neutron skins. Here are the DOM results that I just showed you on the previous slide in a plot where the skin for 48 is plotted as with respect to the skin in lead-208. So this is the box associated with that result. There is a Markov chain Monte Carlo DOM analysis that gives you this box. I'll briefly show you additional results from that. And as you have probably become aware of, there are P-REX2 data now that give you a skin that essentially tells you 0.28, so that's centered here. So this box is not correct as far as the C-REX result is concerned, but it gives you the box associated with the P-REX2 result. We are, of course, awaiting the C-REX result, and we have arbitrarily put this box on this 0.25. That's, of course, to be seen. What is interesting here is that the coupled cluster results for the calcium-48 result is much smaller than the DOM results, either this way or this way, and that's further confirmed by looking at these Monte Carlo Markov chain analysis. for various skins in these various isotopes. The best results are typically obtained when there are partners in isotope chains. Therefore, for lead-208, there is a quite broad distribution here, and it would be wonderful to have additional constraints in the lead region. But you can see the calcium-40 and 48 results give you nice results, a negative skin in 40 and a positive skin much larger than the current coupled cluster results. So this is interesting to be seen, clarified with experiment. Of course, this link between the neutron skin and the symmetry, slope of the symmetry parameter is clearly identified within this well-cited paper. This has been used to make statements between these types of measurements and the parameter of the skin. I wanted to emphasize that this is within the context of density functional theory. We see in a recent paper by Jorge that already there is some tension between a large skin and the dipole polarizability. If you stay within the DFT paradigm, we know that ab initio work in light nuclei tell you that the mean field picture is deficient. And what I have shown you here in effect is that the DOM confirms that also for heavier nuclei. I can illustrate it. I can also skip that. In any case, the DOM should be extended to include response functions to make it even more comprehensive. I'll skip this slide. I just want to emphasize again that strength above the Fermi energy for spectral distributions, even for very deeply bound nucleons, is constrained by experimental data that allow you to give the correct differential cross sections. Mean field doesn't give you the correct description of giant resonances. You have to go beyond it. So it is worthwhile to go beyond the mean field to make this link between finite nuclei and infinite nuclear matter or neutron matter stronger. And one of the things that this dispersive optical model can as well do is to constrain the potential using the energy of the ground state. This is an experimental result. Here is the DOM fit, where it includes that result. The interesting notion that results from doing this is that the fraction of the binding energy from the 10% most deeply bound nucleons is a huge fraction of the total binding energy. So 10% gives you in lead essentially 2/3 of the binding energy, and this can be clearly identified as associated with high momentum content. So that's a notion that is relevant. If you turn this information for the ground state energy calculated within the DOM and compare it with, for example, this argon V18 self-consistent calculation with Green's functions, which gives you a reasonable saturation density, you see that these argon V18 circles for the energy density multiplied by 4 pi r squared gives you essentially consistent results. It also emphasizes that the interior of nuclei doesn't really constrain the binding of nuclear matter very well. There are no particles here, so how can it say anything about that information directly? Of course, people have been using the empirical mass formula, but using the energy densities that we have obtained, we see that we do not get anywhere near this 16 MeV for the volume term. So we are sort of trying to argue with people that it's perhaps a good idea to re-examine this relation between the binding energy of finite nuclei and the equation of state of infinite matter. I'll leave it at that. I will also skip this slide and come to my conclusions. I think you can safely conclude that the DOM can describe many experimental data by simultaneously describing structure and reaction data. It can predict and to some extent successfully generate a large spin for lead-208, which is consistent with the cleanest experimental information we have. It can also be constrained, the self-energy, by the energy of the ground state, and then it will have to include high momentum components, which have been experimentally observed with other experiments that I have no time to discuss in this talk, which also generates a consistent picture where the protons as a minority are more correlated when neutrons are in the majority. And then finally, while not having a lot of time to talk about it, I just wanted to notify you that the 16 MeV canonical value may not be the whole story, and it could well be that a couple of MeV less might be a better way to think about this nuclear matter, symmetric nuclear matter energy curve. In any case, I hope I'm challenging you to think about these things. The C-REX results, of course, I would be happy to learn what they are going to be. It may upend our interpretation or confirm it. It should be interesting no matter what. And as I briefly mentioned, I would like to extend the DOM to also allow an exact representation of response functions, further clarifying the link between finite nuclei and parameters that may have relevance for infinite matter. And with this, I thank you for your attention.
Thank you for an excellent talk. I look on the chat and see that Andrew Steiner has his hand raised. You want to ask your question, Andrew?
Yeah, thank you. So with regard to the two previous talks, since you brought up, effective masses and response functions, I wanted to ask about this, maybe to the previous two speakers and also to the community. As Wim mentioned, part of the confusion around the effective mass is that it's not really an observable. And so it only has a definition in the context of a particular a model of the nucleon-nucleon interaction. But on the other hand, the response functions, which you mentioned at the end, are very strongly the static and dynamical response are dependent on the effective mass very strongly. And of course, the neutrino cross section is an observable, right? In some particular regime. So I guess, is it, what should we do about this? Is the most important thing to make sure our neutrino cross sections are varied along with the effective mass, or what is the advice there?
Well, let me just comment. I mean, you say the effective mass is not an observable. It's not completely correct. I think you can safely say that the effective mass is equivalent to the specific heat if you have a bucket of a quantum liquid like helium-3. The specific heat can be measured at low temperature. We know for liquid helium-3, it's about 3 times the mass of the atom. And there's no doubt that the effective mass then gives you a clear indication. So in that sense, if that's the effective mass you're using, there is a link.
Yeah, but the rest of the interaction also impacts the effective mass, right? The sort of potential energy parts that we think of, right? They also affect the specific heat as well. And so how do you decompose the?
Well, depends on your language, but from my point of view with Green's functions, the effective mass has a non-local contribution, which usually in the language has been referred to as a K mass, and it has an energy contribution, the omega mass, as people have also been. Right. And if you don't do both and don't do both right and check them in finite nuclei, you have to be very careful with what you do in an infinite system. And so I think the effective masses that come from the calculations, the ab initio calculations that I identified very early on, are useful constraints to look at also as a function of density and as a function of asymmetry to guide you along. So that's just my understanding of the situation. That's how I would approach the problem.
Thank you.
And we have another question by Carlos. And while Carlos is asking the question, maybe we can set up the next speaker because we're running a little bit late. So Carlos, go ahead.
Hi, Wim.
Yeah.
I would like to ask you one thing. We have been relying on this relationship between the neutron skin and the slope parameter in the last few decades.
Mm-hmm.
And now we come to this situation which they say the skin is, I think, 0.3 Fermis, right? That's what the press express.
0.28 for lead.
Yeah, so which, from what I read, it eliminates a lot of possible and some of them are thought to be very good mean-field cases. Okay, so you say that DOM could show a better result than some of the mean-field calculations. So do you have any result for that yet, or you are working on it?
So this is the point to make this DOM consistent with infinite matter is a possible project. What we're doing is basically say we have all these data which clearly identify that nuclear physics should be interpreted not with a mean field picture. And all I'm saying is be cautious if you rely too strongly on the mean field paradigm to extract infinite matter results. That's all I really want to say at the moment.
Okay, I think we can discuss more.
Absolutely.
Nice talk, Wim.
We will have. Thanks again. We'll have time tomorrow to discuss a lot of these talks a little bit. The next talk is by Chuck Horowitz. Your slides were good. I see that you're doing something new. I'll let you get set up.
Okay, great. I hope people can hear me and see my slides.
Yes, everything looks excellent.
Okay, great. So thanks for a chance to talk. Wanted to talk about the P-Rex experiment. We're interested in neutron-rich matter. You compress almost anything enough. Electrons react with protons to make neutron-rich matter. And so this is at the heart of many fundamental questions in nuclear physics and astrophysics. For example, what's the structure of many compact and energetic objects in the heavens, and what determines their electromagnetic neutrino and gravitational wave radiations. We're interested in neutron-rich matter over a large range of density and temperature. It's a very versatile material. It can exhibit many different phases. To study neutron-rich matter in the lab, one place to look is in the surface of a heavy neutron-rich nucleus such as lead-208, because we expect to have a neutron-rich skin made of neutron-rich matter. Great, so this is a simple relativistic mean field model for the density in lead. So density versus radius. The red dash curve is the point proton density, 82 protons. The black dash curve is the 126 neutrons. From the protons, you fold the single nucleon form factor, add probably small meson exchange currents to get the electromagnetic charge current, charge density. And so that's the red solid line. You can also get, and I'll talk about that more in a moment, the weak charge density follows mostly from the neutrons, and so the black solid curve is the distribution of weak charges in the nucleus, and the P-Rex experiment is focusing on how much the neutrons or weak charges are expected to stick out compared to the protons. Okay, and we are following very much in the footsteps of Ingo Sick. Ingo, noted experimentalist, and his work on elastic charge densities has had a big impact on nuclear physics. So for example, this is his beautiful charge density for lead. The left panel is the measured cross-section as a function of momentum transfer. It's been measured over 12 orders of magnitude. And one can directly, and that's what Ingo did, deduce the experimental charge density in lead. So that's the solid black lower curve on the right-hand figure. So that's the experimental charge density. So Ingo measured the charge density, and now P-Rex is measuring the weak charge density, given that the electromagnetic charge density has already been determined. So we use parity violation to isolate the neutrons. The weak charge of a proton is small. The weak charge of a neutron is large. So the weak interactions provide this very theoretically clean probe of neutrons. And what we actually measure is the parity violating asymmetry. So it's the fractional difference in cross-section for scattering positive helicity or negative helicity electrons. And let me just emphasize, this electroweak reaction is free from most strong interaction uncertainties. And so this provides a way, in principle, to map out the weak form factor. So capital FW, this is the Fourier transform of the weak charge density, and the weak charge density is very closely related to the neutrons. Oh, great. So P-Rex ran in Hall A at Jefferson Laboratory in Virginia, 1 GeV electrons elastically scattered at about 5 degrees. So the parity violating asymmetry that was measured was about 550 parts per billion. So it's about half a part per million. So the green vertical shaded band in the left, the right-hand figure, that's the P-Rex measurement of the parity violating asymmetry. And a variety of model weak charge densities are plotted as data points. And for each model, we calculate the parity violating asymmetry, fold with the experimental acceptance, and that gives a prediction for the parity violating asymmetry. And we can directly compare it to observed. And this gives us the weak radius. So the experimental result is the RMS radius of the weak charge distribution, 5.8 plus or minus 0.075 Fermis. Technically, that's the average of the P-Rex1 and P-Rex2 results. P-Rex2 had significantly more statistics, so it's basically dominated by the P-Rex2 result. So the weak radius is 5.8 Fermis. You can directly compare that to the well-measured charge radius of 5.5 Fermis. So the difference is a weak skin of about 0.3 Fermis. And then the weak skin is very closely related. It's not exactly identical, but it's very close to the neutron skins. So the RMS radius of the point neutron minus point proton radii is 0.283 Fermis plus or minus 0.071 Fermis. So that's the result of the PREX 1 and 2 experiments. That's the average of the two results. And let me mention one more number. We directly determine the weak form factor, so the Fourier transform of the weak charge distribution at the momentum transfer of PREX2, that's 0.3676 Fermis, plus or minus, excuse me, it's dimensionless, plus or minus 0.0125. So that's the experimental error on the weak form factor. Great, so that's the experimental results. Want to compare this now, talk about the pressure of neutron-rich matter. We're of course interested in the equation of state. The pressure forces neutrons out against surface tension. A thick skin in lead is correlated with the high pressure of neutron matter. Of course, the radius of a neutron star also depends on the pressure. So the measurement of this neutron radius in the laboratory determines the pressure near nuclear density and has important implications for the structure of neutron stars. So a neutron star is 18 orders of magnitude larger than lead, but it's the same neutrons, the same strong interactions, and the same equation of state. Important technical details. Pressure is force per area. If you want to measure a force, the technical way we do it is to use a spring and a ruler. The spring is surface tension. The spring is accurately calibrated by the known surface energy of nuclei. And the ruler, the measurement of the thickness of the skin, that's PREX. Okay, I want to compare the PREX result for the neutron skin in lead. So the upper x-axis on this figure is the neutron radius minus the proton radius in lead. Want to compare that to the radius of a 1.4 solar mass neutron star and to the deformability of a 1.4 solar mass neutron star. Of course, LIGO data from GW 170817 has constrained the deformability, and I've plotted what might be slightly aggressive, but one of the LIGO papers assumes a common equation of state for the two neutron stars in the merger, constrained equation of state to reproduce the deformability constraint that was observed, and then re-express that in terms of the deformability of a 1.4 solar mass neutron star, even though the actual masses may not have been exactly 1.4 solar masses. Okay, so the LIGO results favor the lower region in this figure. The nicer radius for the pulsar that's near 1.4 solar masses, basically about 13 plus or minus 1 kilometers. And then finally, the PREX2 result for the skin in lead of around 0.27 Fermis. And the so what we're doing when you compare the lead skin to the neutron star quantities is you're probing the density dependence of the equation of state. The neutron skin is of course sensitive around nuclear density or slightly below, and the radius and deformability of a neutron star are sensitive around 2 times nuclear density. The blue circles are a collection of simple relativistic density functionals with a straightforward density dependence, and in particular, a density dependence that doesn't have any phase transition. So there's slight tension between PRX2 and LIGO. PRX2 is favoring larger neutron star radii, for example, than is LIGO, but there is certainly a region of overlap, and the separate results are not inconsistent. Okay, so that's the PRX2 result, and it's basically favoring a slightly higher pressure. Okay, and want to mention a second experiment. So PRX measures the weak radius of lead-208. CREX experiment is very similar to measure the weak radius of calcium-48. Calcium-48 is a smaller nucleus. It's more amenable at this time to microscopic calculations, and it provides a more direct comparison between chiral effective field theory predictions and cleanly measured neutron properties in calcium-48. So of course, chiral effective field theory has three nucleon, in principle 4 and more nucleon interactions. It's an expansion in powers of 1 transfer over a chiral scale. 3 neutron forces, that's the important quantity we want to probe. The 3 neutron forces are important for the pressure of neutron matter, especially as one goes up in density. These 3 neutron forces are hard to directly observe. They increase the pressure of neutron matter, and they increase the neutron skin thickness of both lead and calcium. So the PRX measurement in the larger lead-208 is better for inferring the pressure of neutron matter, and so more direct comparisons with neutron star properties. CREX measuring the neutron skin in calcium-48. The smaller system allows direct comparison to microscopic chiral effective field theory calculations in the finite system. And again, it's very sensitive to 3 neutron forces. Okay, so the CREX experiment data taking is complete. Analysis is underway, and the present plan is to announce results at the October American Physical Society Division of Nuclear Physics meeting. So let me end with just an illustration. So what's plotted is the neutron skin in lead on the x-axis. So that's the neutron minus proton radius of lead. The PRX result is shown with the black error bar. And then the y-axis is the neutron skin in calcium-48. The original dispersive optical model prediction, so what Wim was talking about in the previous talk, is relatively large for the skin in calcium. And then so that's the upper band. The red circles are a series of non-relativistic density functionals, while the blue squares are a series of relativistic density functionals. And not too surprising, there's basically a correlation. A thick skin in lead is often correlated with a thick skin in calcium. The lower error band is the chiral effective field theory calculations Hagen et al. So this is the Oak Ridge group. So this uses a coupled cluster expansion of the wave function for calcium-48. And this predicts a very thin skin for calcium-48. And given the P-REX2 result, the simplest explanation or possibility would be that this chiral effective field theory calculation is probably wrong, and that the C-REX may get a thicker skin in calcium because P-REX found a thick skin in lead. But we will see. And again, we expect to announce results in October. So in closing, let me just emphasize a really good graduate student. So Brendan Reed has contributed several results of this talk. So thanks very much, and happy to take questions.
I don't hear Chris, so maybe I'll pipe in just for the sake of time. Chuck, you've seen the PG
Sorry,
Reinhardt.
yeah, go ahead. Sorry, Andrew.
No, that's
I was on
okay.
mute.
You've seen the PG Reinhardt preprint that analyzes the P-REX2 data and arrives at a lower value of this, the density dependence of the symmetry energy L. Do you want to comment on that?
Not really, but I will.
Okay.
So the P-REX collaboration stands by our result. So the result for the thickness of the skin, and actually let me come back and I guess I didn't talk. So this is the symmetry energy. Its density dependence is this parameter L, and basically the P-REX2 result for L, if you believe the correlation between L and the surface thickness, is around 110 plus or minus 40 MeV. So the P-REX2 result is big, but it's with a significant error bar.
Sure, thank you.
Carlos, do you want to ask your question?
Hi, Chuck. Would you please go back to the transparency where you show the electron scattering data from INGO-seq? So probably you have got this question many times. Here you have experimental data with many orders of magnitude, and this is necessary to unfold the form factor so that you can get this figure on the right with certain certainty, because this is not an easy task. There are some model dependence on how do you expand the density and so on to get this unfolding of the form factor. Now you have from the P-REX experiment just 1 point. So when I compare with the experimental data from electron scattering, you are making very strong statements based on 1 point and the Fourier transform of 1 point. How can I understand that you are so sure about this result?
Yeah, so great. Let me talk about that. First of all, INGO's beautiful data. By measuring out to 3.5 inverse Fermis, they're able to directly determine the elastic charge density, and in particular, the density at small r is the most difficult thing to determine.
Right.
So determine the radius near r equals 0, and he had to blow up the figure to finally see the experimental error in the charge density, and that's this little region there.
Right. Right.
So the short answer is we can't, even in our wildest dreams, think about determining the weak density near r equals 0 in lead. We may be able to do that in calcium-48, and so we've published a paper on what it would take to actually do that for calcium-48, but we certainly haven't done it and probably can't do it for lead.
Right.
So if I could show you what we have done. And so we measure at one low q-squared point. We're interested in a radius, and technically the radius is the derivative of the form factor as q goes to 0, and you can't measure it q equals 0. So we have a very small dependence on the surface thickness of lead. And so the weakness, the thickness of this correlation, the distance from there's a dotted red line down there to a dotted red line up there, that depends on varying the surface thickness. So we've assumed an uncertainty that includes a whole range of microscopic models. So that is what we call the model error. And this thickness gives a very small error to the extracted weak radius. In the PREX2 paper we quoted, it's about 0.015 Fermis, and that's much smaller than the experimental error, which is just dominated by statistics.
Okay. Okay, thank you for the explanation.
Sorry, Catalina, if you would like to set up, that would be great. I keep on muting myself for some reason. Yeah, I had a quick question for you while Catalina is setting up, which is, did they include the, for the LIGO estimate for that radius, did they include the uncertainties in the masses of those of the neutron star? Is that all included when you get that less than 13 kilometers?
So the LIGO published an upper limit for the deformability of a 1.4 solar mass neutron star. And so that was just a little less than 600. So our 13 kilometer limit on the radius is based on just looking at a variety of density functionals and seeing what this upper limit of the deformability of 600 means for the radius. And it's an upper limit of about 13 kilometers.
Thanks. Okay, we should move on to our next talk, which is by Catalina on low energy kaon nucleon experiment studies. Catalina, your slides look good. Take it away.
Thank you very much. So first of all, let me thank you for accepting me to this very, very interesting workshop. And now I'm going to speak about something rather different of what we heard from before, because we are moving towards strangeness. And what I'm going to show you is experiments studying the low energy interaction of the strange particles in form of kaons at our collider, which actually is at 100 meters from my office. Right now I'm in my office in the Daphne Collider to show you how we are studying and what type of studies are we doing in the interaction of strangeness with nuclear matter to actually measure how strong this interaction is, and this can and is contributing also towards the study of the strangeness possible contained in the neutron stars in various types of forms. So this is our collider seen from outside the Daphne machine. I'm in the office just here. You can see here the corner. And the type of physics we are doing in this collider right now, we are in the measurements. I'll show in some minutes of transitions in kaonic atoms. And by this, you can study the interactions threshold and actually measure how strongly the interaction of kaon with nuclear matter, starting with the nucleon, is at threshold. We are also measuring interactions with nuclei in forms of scattering and nuclear interactions. And of course, that while doing this has a very strong impact in studying the strong interaction, which I quote here some of our papers and some of the directions our research is impacting into. Of course, the QCD, like chiral symmetry and lattice calculations, chiral symmetry breaking, and so on and so forth. And also this has an impact in the equation of state of neutron stars and in astrophysics, because there are some models and theories which are looking into the strangeness role which might be ongoing in the neutron stars. There are discussions here which I'm not going to touch, but I'm only going to show you how we study and how we measure interactions of kaons and of strange particles, hyperons, with nuclear matter, which has an impact in this discussion, which is bearing on what possible role strangeness might have and play inside the neutron stars, going from heart of neutron stars up to recent discussions about the possible second family of neutron stars, which actually are not neutron stars, but might be the strange quark stars. And I've seen that there are some talks related to this, mostly, if I'm not wrong, in the day of tomorrow, which are touching this type of item. For what we are concerned, we are experimentally studying the type of physics going under kaonic atom spectroscopy. You see here part of our team, which is installing the apparatus where we stop kaons delivered at the Daphne Collider, and we measure the transitions in these exotic atoms by measuring the radiation in form of X-rays produced when these atoms are formed in highly excited states. Then they go towards eventually fundamental orbit. So a very brief introduction to the physics of kaonic atoms is that what we do is we stop kaons delivered from a machine. In our case, we are lucky because our kaons delivered at Daphne, which is an electron-positron collider optimized at the 5 resonance, are already with starting with very, very low momenta. So that's very, very peculiar, because it has a huge advantage with respect to extracted kaon beams like Japan, previously at Keck, now at J-Park, where kaons are high energy. So you need to, if you want to stop them, you need to put a high degrader, so rather sick degrader, and then you lose quite a lot. So kaons are stopped inside the target, they are captured, replacing the electrons. While doing so, they form highly excited exotic atoms, which then, according to some yield, which depends on many components, some part of the kaon succeed to make it through the fundamental level, especially in the light kaonic atoms, and we measure the X-rays produced in this, the excitation process. These are very rare processes because the yield can be as low as 1% or even less for kaonic deuterium if you want to study the decay to the fundamental orbit. And we do so because on the fundamental level, on the top of the QED, you have the strong interaction effects, which are actually inducing a shift and the broadening of this level with respect to what preview or calculated, applying only the QED. So if you compare the measured radiation, so the X-ray spectrum, what you measure, with what predicted from only and only QED, what one can extract are the shift and the width induced by the strong interaction, I repeat, with respect to the QED calculations. And so the measurement compared to the QED calculation delivers the strong interaction contribute, which is in the form of this shift and broadening, so the width of this level. And these are related in turn with the information relying with isospin-dependent scattering length in the anti-kaon nucleon interaction from the kaonic hydrogen and kaonic deuterium. We have also measured kaonic helium. I'll come shortly to this in a moment. So these are the measured quantities, observables, the shift and the width, which can be related with the scattering lengths, anti-kaon, isospin-dependent anti-kaon nucleon scattering lengths, which are not so easily extractable, but there have been improvements in late years with respect to the original DESER formula. There have been introduced some corrections which are belonging to the isospin breaking and next to the leading order corrections, which show the way to go, if you have precise measurements, to go towards extraction of these isospin dependent scattering lengths, which are the fundamental quantities which help to tune the QED and the QCD with an impact also in the physics of the neutron stars. And what you can get out of here, so out of this, it's of course phenomenology of the low interaction anti-kaon nucleon phenomenology, threshold amplitudes, also the lambda 1405, which is a kind of a prototype for whatever might be, if any, the deeply bound kaonic nuclear states, which now it's an ongoing discussion. And through the determination of the anti-kaon nucleon sigma terms, one can get also the degree of chiral symmetry breaking and so on and so forth. Moreover, once one gets this information, one can also eventually access something about this contribution of the strange matter inside the neutron star, so towards the equation of states which contains strangeness, including this hyperon puzzle in the neutron stars. Experimental wise, we use the Daphne collider, which is a machine which is rather complicated because on a circumference of about 100 meters, it contains 200 something magnets. There are actually two rings, one with electrons, one with positrons, where collisions of electrons with positron beams are produced, tuned at phi energy, which is producing the back-to-back K plus K minus in half of the times in its decay. So since phi is produced at rest, this also means that kaons are very low energy, which is, as I told you already, it's a very, very good for us who wants to start already with low energy kaons, because then we can stop them rather easily, degrading them in energy with only a couple of microns of millimeters of plastic as a degrader and not meters of degrader. So that's a very, very big advantage, and it's suitable to study indeed the low energy physics phenomenology and to quantify it. So to measure how strong it's the strong interaction between archetypal strange particles like kaon and hyperons, as I'll show you in a moment, and the rest of the nuclear matter. We have started to do so within an international collaboration, which was called Siddhartha early this century. So we have done the first measurement kind of 10 years ago, and we have done so using as radiation X-ray detectors, silicon drift detectors, which actually are produced in were produced in Germany. Now we are using detectors produced actually in Trento at the same motherhood of the ACT stars, so FBK, so the Federazione Bruno Kessler. But these detectors we used in the previous experiment, which we're pioneering with PN sensor in Germany, are for the first time used to do spectroscopy. You see, however, that we had a problem here, that active area with respect to total area was less than 40%. So that was a limitation which now we are overcoming. That's a kind of an animation. So we do the phi decays in kaons. We stop kaons in a target which forms atomic kaonic atoms which deliver X-ray, which we measure by silicon drift detectors. And the first measurement we have done already 10 years ago, we're measuring the kaonic helium, in this case, not on 1s level. This is still too difficult because the yield is very, very low, but we stopped to measure the 3D to 2P level transition, which was kind of a puzzling data coming from old experiments, which were showing apparent high shift on this level, whether no shift or basically less than 1 electron volt was expected from theory, where the strong interaction is not expected to extend to the 2P level. It's too far to say so from the nucleus. So that was very puzzling because a measurement of 40 electron volt with respect to theory, which predicted something like 1 electron volt puzzling. So we have done this measurement. Previously was already done by a tech before us, but we have remeasured this transition. You see here how nicely the conic atom is shaped. This is only calibration spectrum where no counts are produced, so we use this for calibration, and we have done the remeasurement of the conic helium-4, and the very first measurement of the isotope twin conic helium-3 transition with electron volt precision. That was the very first ever, and we could actually assess that the old experiments were wrong. These are our publications, and we are now going into precision era, which we hope to go further on, because this does not yet solve the difference between various theories, which are actually predicting, some of them 0.1, other 2 electron volts shift, which is not yet solved by present measurements. But at least we can easily say that wrong conclusions were drawn from old experiments. We have done the most precise experiment on the conic hydrogen, which extracted actually the sum of the isospin dependent, half sum of the isospin dependent, because the interaction of the proton combines the 2 isospins. So this also means that below this measurement, which is the most precise one, we also need the deuterium now to extract the individual interactions with the proton and the neutron of the kaon, of the negatively charged kaon. And to do that, we set up a new experiment, which is ongoing right now, the conic deuterium in Siddhartha 2. The theory is spread all over, so if you look at the shift and the width of the predicted in theory, so theoretically predicted shifts and widths are spread all over. And that means that an experiment is badly needed to solve this theoretically puzzling situation, which also sets the ground for knowing the prototype of the strangeness interaction with the nuclear matter. And we extended our collaboration also with European funding. We extended Strong 2020 to more partners, also coming from from Croatia and from Poland and from Japan. And we built up a new experiment. Now I'm not going to bore you with the features of the new experiment, which contains 2 levels of veto system to be able to reduce the background, but also contains brand new silicon drift detectors for the X-ray measurement, which have a much better active area over overall area. And that's the group, the team which installed the first part of the experiment on the machine last year. We were stopped due to the pandemic situation for 1 year, but we have restarted a couple of months ago, fortunately, to quantify and to qualify our apparatus, which again, the conic helium measurement, which is rather easy, so such as to go, once we have quantified and qualified our apparatus, to this very difficult measurement, never done before, of conic deuterium. And right now, I told you we are in a first phase of the experiment with 1/6 of the apparatus to quantify and to qualify the new machine. That's the apparatus installed with the shielding on LED on the surroundings. And what we have done was to work with this apparatus while machine was, so the Daphne machine, it's starting up and it's in a optimization phase, so we are optimizing together. And it's very nice because we already regained the very nice situation on the conic helium, and we didn't yet use the veto systems. So we are very confident that now we will go towards the conic deuterium setup, integrating all the detectors and everything else. Here it's without trigger, here it's with trigger. We have a rejection factor 10 to the 5th, but we will have an even stronger rejection factor with the veto system we set up in the second phase. So we will install the apparatus this summer, and we will start hopefully to take data to go through at least half of the next year, also to integrate this measurement of conic deuterium, and that's our simulated spectrum with achievable precision, and that's how it will stay on this map of theories. So that's our targeted precision. Of course, we don't know where it stays, might be here, might be here, might be here, or might be exactly where it stays, which will be very, very interesting because this really pins down the interaction of strangeness with nuclear matter. And we are also preparing a proposal for future measurements, which are also being used. If you want to know more, we published a couple of months ago this document towards a future proposal of additional conic atoms, heavier and lighter, and also nuclear interactions of various sorts and type, including interactions of hyperons with nuclear matter. And again, that's a paper we published with a kind of more, let's say, outreach target about what type of measurements which we are doing. And on the other side, we have another collaboration, which is called Amadeus, which is looking into the nuclear interaction, trying to, and actually studying the interaction of the hyperons with 1 or 2 nucleons and very low momenta, and also the controversial lambda 1405. And we do this reusing data from an older experiment, Chloe, which had a different aim to study the neutral counts interaction, but we are using the charge counts part in the form of nuclear interaction of K- with the matter, which is in the drift chamber. And we have succeeded to actually do very nice measurements. We have also inserted pure carbon target and studied the interaction of kaons with carbon nuclei. And what we have done here, I jumped to only show you what we have published in this paper, which is quoted here. One, it's interaction, the channel, which is sigma 0 with the proton, where we were also looking for the deeply bound state, which we couldn't find, but we found very interesting cross sections, which we complemented with the lambda proton in this paper published in 2019. So we have actually characterized a whole series of lambda and sigma 0 proton and in 2-body and 3-body and 4-body nuclear interactions, which could be used and should be used for understanding also the equation of states of for the neutron stars. And we are also aware that there is a desert in this type of studies. Like, for example, you see here 2 types of channel. One is the elastic, one is inelastic channel, which also bear on the fact that this impacts also in the equation of state of neutron star. And for the future, we want also to have an impact here and use the power of Daphne, which delivers kaons with the momenta below 120 MeV/C, exactly where there is the desert, and we are preparing a setup which contains a TPC and a type of liquid scintillator for neutral particles to complement and to fill in the gap also in this sector. So in conclusions, it's we are performing a lot of studies on the low energy kaons, low momenta kaons, to characterize the low energy quantum chromodynamics, so the QCD at very low energies, which has also an impact in the sector of the neutron stars. If you want to know more about our plans, I can only refer to this link on the workshop we have done in February this year, where we have discussed all these things, and I invite you to have a look there. That's again a picture of our collider seen from outside. And thanking you, I invite you maybe to come to see you in Frascati. Hopefully we will be able to organize a workshop again soon. And I hope we can meet in person in Frascati and discuss these fascinating items and issues, including the way we can contribute and shape our contribution also towards understanding better the neutron or the strange stars. Thank you very much.
Thanks a lot, Catalina. Questions for Catalina?
Yeah, it might be a bit more difficult because that's quite a different type of sector. But what I can hope is that people might be curious and have a look into what we are doing and come up with ideas and suggestions also for our future measurements and implementation of part of our measurements towards the studies which are also relevant for the neutron stars. Did you fall asleep?
I have a question. I have a more general question, and I don't know if you're the right one to answer this, but when we're looking at some of these strange stars, it used to be we thought they could produce these kind of more compact objects, but then it was realized, I thought that if you might have strangeness in the core, but you wouldn't have strangeness on the outside, and the radii of neutron stars produce these strange stars would have this outside area that still had a radius that was not so different than what we're getting for neutron stars. Is that the case, or is there any way we can, like, is there a measurement from the astrophysics point of view that can help constrain this strangeness?
Yeah, I'm not so sure I can answer to your question from astrophysics point of view, but what I know is that people who are working in the strangeness nuclear part of physics, astrophysics, what they are requiring, it's mostly interaction of lambda, sigmas, and all these strange particles with more than two nucleons, and that's what we are trying to do. But from the astrophysics point of view, I'm not the right person. I know that there are many persons discussing this and even debating, because the question is not, as far as I know, yet settled. Maybe there is someone who can counter comment.
Jürgen,
oh, I see Jürgen Schaffner. Maybe Jürgen is the right person.
Yeah, hi there.
Hello.
Thank you for raising this question. I mean, this is an unsolved issue about the presence of hyperons, which is not sure and hinges essentially on the hyperon-nuclear interactions. But there might be also kaons in the game, and then we need to understand the kaon-nuclear interaction, right? So it could well be that hyperons are present, but they cannot be measured with the mass-radius relation, because the mass-radius relation is a measure of the equation of state, which is composition blind. Gravity is composition blind, so you cannot measure hyperons with gravity. So what you need to measure the hyperons, the presence of hyperons in neutron stars, we need to look at astroparticle physics aspects, which means cooling, for example, for neutron stars. So cooling is different whenever hyperons are present or not, for example. Or for R-mode instabilities, which is also driven by hyperons, stuff like that. So it's actually a very subtle issue which cannot be answered by looking at the mass radius curve alone, I think.
Thank you, Jürgen.
Yeah, you're welcome.
I think we should probably, we're running late, so we should probably start setting up the last talk, which is Wendell Misch on a completely different topic. If there's any other questions while he's setting up, feel free to ask. And if not, Wendell, you can take it away with your talk on astrometers and the R process.
Sorry about that. I was trying to figure out how to unmute myself once I was in the share screen view. All right, is this all visible?
Yes, I can see your slide.
Okay, great. Okay, so yes, can I talk about astrometers in the R process? Astrometers being a neologism coined by my collaborator, Calvin Johnson. So pause for camera here, and let's get into it. So astrometers are astrophysical isomers, and those are going to be ingredients in astrophysical nucleosynthesis. Now I have up here a Big Bang nucleosynthesis network, obviously not related to what we're talking about here, but it gives a sense of what a nucleosynthesis network looks like. You've got, in this particular little network, we've got 8 nuclei, and they are connected by various nuclear reactions. And these network calculations require all kinds of careful nuclear physics inputs, including nuclear masses, cross sections, reaction rates, decay rates, etc. Let's look at a particular nucleus that is well known for an isomer. It's not going to show up in the R process, but it's a very good example to study. So normally what we've got is the situation where nuclei are complicated things and we need to find some simplifying assumptions to put them into a network calculation. Usually what we'll do is either use the ground state properties or assume a thermal equilibrium distribution of excited states. Aluminum 26 can be a complicating factor though, because it does have this isomer at 228 keV. And an isomer is an excited state which lives much longer than a typical excited state due to some quantum mechanical mismatch with lower states. In this case, that mismatch is the large difference in spin between the excited state and the ground state. As a consequence, transitions to ground are inhibited and also transitions from ground are inhibited. In astrophysics, aluminum 26 we care about because it produces a nice signal for a tracer of star formation. And this ground state has a nice half-life of 700,000 years. But the excited state has a half-life of 6 seconds. And so if we want to understand how this is produced in situ, we really need to understand the beta decay rate of this thing and how the ground state and the isomer communicate with each other. In this case, we can't really use a thermal equilibrium distribution because if you're too cold, this transition is inhibited. The isomer will decay away faster than it's repopulated. But neither can you use the ground state necessarily, because if you produce and you land in the isomer, you can't de-excite and get to ground. So you've got to treat these as separate species in some way. We do that by considering the nucleus as a graph. So in this case, the ground state is state A, the isomer is state B. We don't really have a transition between the two, but what we can do is make a transition from state A up into one of these intermediate states. From here, you can random walk around a bit, and then if you transition back to A, that's a failed transition, but if you transition down to B, you have successfully transitioned from A to B. And of course, we can reverse all the arrows and look at transitions from B to A. We'll define this P here, this capital P, is a probability that if you're in, say, state I, it's the probability that you get to state B eventually before you get to state A. With that, and these little b's here are transition probabilities. If you're in, for example, if you're in state A, then this BAI is the probability that your next transition out of A is into I. And we can set up a system of linear equations to get these probabilities, which will then give you your rates. And it's a nice linear system. It's easy to solve with an equation solver. Let's look at the results for aluminum 26. Now, what I'm going to do, and part of the reason I picked aluminum 26 is I can step through adding lines to this figure one at a time, which will make later figures make more sense. So this is just the beta decay rates for aluminum 26. You've got the ground state in red and the isomer in green. That will be consistent throughout all the lines we've drawn here. Reds are transitions or decays out of ground. Greens are transitions or decays out of the isomer. Here is the thermal beta decay rate. So if we allow a thermal population distribution, then the isomer will eventually start getting populated right around here, 10 keV, and it will drive up that thermal beta decay rate. But here's the actual transition rates that we calculated. So green is transitions out of isomer to ground, red is transitions out of ground into isomer. And what you can see is that the transitions which populate the isomer between about 10 keV, well, basically anywhere below 35 keV temperature, are much slower than the thermal beta decay rate. So that tells you that the isomer is not being populated rapidly enough to keep up with a thermal decay rate. And so there's something funny going on. You got to be careful here. So this black shows the steady state beta decay rate. If you take a sample of aluminum 26 and set it in a high temperature and let things come to some kind of equilibrium, this is the decay rate that you'll see. And you can see that below about 15 keV is just the ground state rate, but then it kind of tracks the transition rate into the isomer until eventually you reach thermal equilibrium. So you might think that, all right, so below 15 keV or so, which is where this particular nucleus is relevant, we can just use ground state, but that's not really true. These green triangles show the steady state rate if you have production, a constant production directly into the isomer. So again, this shows that anywhere below about 35 keV temperature, you got to treat these as separate species. So above 35 keV, this thing is thermalized. You can just use a thermal equilibrium population distribution. Below about 35 keV, these have to be treated as separate species. So let's look at some R process stuff. And of course, we're here mostly to talk about neutron star mergers. Here's a solar R process abundance pattern. We've got the first peak in blue, the second peak in red, the third peak in green. We'll be using these colors again later on. The peaks, of course, are where show where the most abundant nuclei are. So you kind of want to look in the peaks for influential isomers or astomers. Fujimoto and Hashimoto did this. They chose 9 nuclei in the second R process peak, and they looked at a few different cases. So this figure is time in days, and on the vertical axis, we have heating. They look at 3 different cases of 3 different values of electron fraction, which are the 3 different panels, and 3 different cases for isomer behavior. In the red, all nuclei were considered to decay only from the ground state. And so no isomer exists, essentially. In case B, for those 9 nuclei, they say no ground state exists. We're just going to use isomer properties. And in case C, they selected 4 specific ones to see if they estimated that those were the most influential. And say, all right, for these 4, they're isomer only, and for the rest, it's ground state only. And you can see they found quite a difference in the heating, depending on how these isomers behave. This can, of course, impact nucleosynthesis and the observable light curve. But they only looked at 9 nuclei. So what we wanted to do is say, what happens if we are agnostic and we select all isomers? So this shows all measured isomers with half-lives greater than 100 microseconds. We computed the transition and beta decay rates for everything on the neutron-rich side. So everything southeast of the line of valleys of beta stability here. And we put those into a decay network. And Trevor Sprouse will talk more about this on Friday, but essentially what we do is we take that R process, solar R process abundance pattern, move it to a very neutron-rich region, and then just let it decay and see what gets populated. And this is what we found. We found all of these isomers here get populated. So what we show here is this quantity R, we're calling it a ratio. It's the abundance of the isomer divided by the abundance of the total abundance of that isotopic species. And again, we've got our color scheme here. So you can see that there's a lot in the second peak that are getting populated, quite a few in the first peak and a handful in the third peak. So we've got all these that are populated, but does populated mean important? And we need to assess that out. So we developed a metric called the astromer importance rating. And it's the product of activity times imbalance times the ratio. The ratio is as I defined above. Activity is a product of abundance times kind of actions per second. An action can be a transition or a decay for the isomer. And this gives you a quantity which is essentially actions per baryon in the material for each species. Imbalance quantifies how far out of thermal equilibrium we are. In thermal equilibrium, if there's a thermal equilibrium distribution between the ground state and the isomer, imbalance is 0. And if you're all in isomer or all in ground state, then imbalance is 1. And so these gives us a number of filters. The activity filters out things which are not present in doing something. Imbalance filters out things which are in thermal equilibrium, and ratio filters out things that maybe get produced in the isomer, but that rapidly decays to the ground state. And so it's not really influencing your environment. What we have in this figure is for each time step in our simulation, we identify the top 5 astomers according to our metric and plot them for all time. Again, we've got these colors correspond to the various peaks. And you can see once again, a handful in the first peak, quite a few in the second peak, and a couple in the third peak. The highlighted ones here are the ones that Fujimoto and Hashimoto found. You'll notice that there's only 4 of them on here, despite their having handpicked 9. And of those 4 that are on here, one of them is hardly influential at all until very late times. So this tells us that our metric is doing something for filtering that handpicking is a hard time doing. And then these highlighted ones are ones I'm going to zoom in on a little bit later. It's going to be Krypton 85, which you can see is really important at about a day. Antimony 128, which is really important on the few hours time scale. Tellurium 129, which is important on the weeks and months time scale. And then I've also not shown on here, because it doesn't show up in the top 5, as Xenon 131, but it does show up in the top 10. So here's what happens when we examine the heating for isomers, or with astomers and without astomers in our simulation. What happens is that some astomers will speed up heating and some astomers will slow down heating. And so you can get this variation in the heating curve that kind of goes back and forth across the without isomer scenario. We classify astomers according to how they influence this heating curve. So accelerants move heating to earlier times. They speed up the heating. They accelerate the decay. Batteries tend to hold on to population, and so they slow down decay and store energy to later times. And neutral astomers don't really do either of this, but they may still generate an interesting electromagnetic signal. An example of an accelerant is antimony 128. In the case of antimony 128, the tin 128 beta decay feeds the isomer almost exclusively. And the isomer decays very rapidly on about the 10-minute time scale, whereas the ground state decays on the 9-hour time scale. So this allows the tin 128 beta decay, which has a half-life of about an hour, to effectively skip over antimony 128 and go right to tellurium, which can greatly increase heating on the hour to time scale. Let's look at, let's see, this is, everything's covering, right? I can't see. This is tellurium, I believe, tellurium 129. This is a strong battery. You can see that the beta decay of the ground state, or the isomer rather, is much slower than the ground state. The antimony 129 beta decay feeds the isomer at about 60%, so a little more than half lands in the isomer. And this slows the beta decay down from about 70 minutes to about a month, which has a strong impact on early heating, and that it slows it. We get that release, that energy release much later on the month's time scale. And then finally, we've got Xenon 131, which is stable. So it does not really affecting heating, the decay of this thing. You're getting just a small amount of energy out of any gamma rays that you get out of this. And it's not fed very strongly. Iodine feeds it at about 1% through beta decay. But it's got a 12-day half-life, and that 1% population could give you a possible electromagnetic signal after an R process event in about the 2-week time scale. So what I've shown you is kind of lines with no width. These are exact in a sense, but that's not really accurate. So what we want to do is examine how things change when you vary transition rates, the unmeasured internal transition rate. So this is Krypton 85. This, I'm not sure, I have the wrong version of this figure here. This should be much wider. What we did was we varied measured rates up and down by 2 standard deviations and theoretical rates up by factors of 10 and 100 to generate the dark and light bands respectively. And what you can see is these uncertainties affect the freeze-out temperature. The freeze-out temperature being when the transition rates are dominated by the beta decay rate. So you get a few keV uncertainty in the freeze-out temperature for this guy. Here's similar bands for tellurium 129 and xenon 131. Again, we did the same thing for the variations. And again, the uncertainties are affecting how these guys freeze out, which can affect the observational consequences. Finally, here's the uncertainty bands for antimony 128. So antimony 128 is a bit of a disaster in the sense that we don't have any transitions measured which connect the ground state to the isomer. All measured transitions either are connected only to the ground state or are connected only to the isomer. Furthermore, the energy of this isomer is uncertain. It's probably less than 20 keV, but it's not really known. And this is one of the most influential astomers in the first few hours. And we have these great big uncertainties. This is driving some experimental campaigns. We have accepted campaigns at Argonne and at CERN to measure these properties in antimony 128 because of it's so influential and so poorly constrained. So we're just getting warmed up on this astromer stuff. So far, I've only shown you effects from electromagnetic transitions and from beta decays. We also need to incorporate things like neutron captures, alpha decays, fission, and anything else that would be appropriate for nucleosynthesis. We need to put this into a realistic simulation. Our decay network is very, very useful for filtering out astrophysical uncertainties from nuclear physics uncertainties. But we need to combine these. And then we need to use that to make robust predictions of observable consequences. To do this, we need a lot more data. As I said, we're actively partnering with many members of the experimental community. We've got accepted campaigns to look at antimony, as I mentioned, also looking at krypton-85 and a number of other nuclei. For the nuclear data, there's a whole lot of unmeasured beta decays or beta decay feedings. So in our simulations, since we don't know the beta decay feeding of gallium-77, we assume it all goes to the ground state of germanium-77, but that's probably not true. It almost certainly feeds the germanium-77 isomers. We need those numbers as well. There's a lot of unmeasured intermediate transitions. That's what I was showing you before. We vary the intermediate transitions and we end up with these widths on our effective transition rates. We would like to get capture cross sections on excited states, and that's starting to happen. Of course, the experiments are difficult, but my experimental colleagues are telling me that's something they're making a lot of progress on. And then there's almost certainly a lot more isomers to discover than the ones that we've included here. We've got a lot of blank areas in here on the neutron-rich side. We've got a big clustering down here on the A = 130 peak, so it's not surprising that those are the ones that were showing up as influential. But there's a whole lot more possible that are very likely going to fill in this area. And that's corroborated by this figure here, which shows the discovery of isomers as a function of time. And you can see it just keeps climbing. Here we are at 2020. And so what's going to happen when FRIB turns on? We're going to see a whole lot more isomers in addition to all the other nuclei that they expect to find. So to wrap it up, isomers can in fact impact astrophysical nucleosynthesis. When you're at a temperature which is below the thermalization temperature, you must treat the ground state and the isomer separately. When that's the case, you have a isomer which maintains its metastable properties in an astrophysical environment, making it an astromer. This can affect isotopic composition and electromagnetic observables. We're currently implementing this in our process nucleosynthesis models, and we are working with experimenters to fill in missing data, and we are developing our techniques to incorporate more nuclear reaction processes. And with that, I'll take some questions.
Thanks a lot, Wendell. It looks like we have a question already up from Jolie.
Fantastic talk. Thank you very much. And thanks for giving a shout out to some of my collaborators, in particular, Kelly Chips and Steve Payne. As you probably know, both Kelly and Steve have measured neutron transfer on both ground states and isomers, most recently of potassium-38. Now, that's not quite the our process, but I think it's meaning they were advancing the techniques.
It's it's important in the RP process, which is it's basically to inform P gamma rates. Yeah.
In addition, you don't have her listed here, but many years ago at Oak Ridge, we measured the DP reactions and also heavy ion induced transfer reactions with neutron transfer reactions on tin 130. And so that is in our process nucleus. It's a very important nucleus. And in the DP reaction, we measured the DP reaction on both the ground state and the 7- isomer.
Oh, that's very exciting.
That's work that's being led by Kate Jones at the University of Tennessee. We are fighting referees to get it published, so hopefully that'll get published soon. One thing that we are missing in that nucleus is we were unable to identify any transitions which connect the states populated by transfer above the isomer to the states populated by transfer on the ground state. So we won't have neutron capture rates on that because we didn't measure the gamma rays in the DP reaction. But that's actually a nucleus which, you know, we have already studied.
That was tin 130, you said, yes?
That was tin 130.
Okay, I'm taking notes here because
I thought you might want that. And the other one is that in many of these nuclei we're studying near closed shells, even if the beam may not have isomers, the population of our final nuclei have isomers. And that challenges our analysis, in particular, the one that I show today, the selenium-83, has a ground state and a 1/2 minus isomer, which effectively can be treated as a separate ground state. So that's the final nucleus we're populating, not the initial one. But so I think you've got some great people, and reach out to Kate Jones. And actually, I'd appreciate a copy of your talk as well, because I found this work fascinating. So thank you very much.
Well, thank you very much. I appreciate it.
Any other questions for Wendell? I'd like to thank all of you for sticking through to the end. I know I allowed it to run late, but we had so many great questions. I'd like to thank all the speakers of this session, and actually everyone contributing to this session. It was a great session. If there's nothing else, we'll meet again tomorrow. Oops, yeah. Talk to you all tomorrow.